Добрый день, коллеги.
Здравствуйте.
Доброе утро, коллеги.
Здравствуйте, Сергей Игоревич.
Так, телетрансляцию в YouTube. Трансляция.
Женя, можно вас пока спросить?
Да?
Можно спросить вас пока?
Конечно.
Короткий вопрос. Вот если будут в основном русскоязычные, может быть, говорить по-русски понятнее будет?
Да, я думаю, что если не будет иностранцев, то смысла говорить по-английски нет никакого.
Ну да. Слайды у меня на английском. На всякий случай.
Нам для публикации важно именно, что человек выступил, а с точки зрения уважения международной аудитории, чтобы либо синхронный перевод, либо слайды по-английски.
Понятно. Ну, оно по-разному в каждых странах. Китайцы могут спокойно половину международной конференции по-китайски выступать и рассуждать. В Австрии, в Швеции немецкий бывает, но в Швеции шведский, но редко. В основном все очень хорошо говорят по-английски.
Но мы таким образом нашу русскоязычную аудиторию немножко воспитываем.
Это да. Но вы знаете, когда разговариваешь с людьми 65+, вот мне 67, то иногда возникает тема там, и патриотизма, там, и самосознания и прочее, что иногда надо и по-русски.
Поэтому у нас присутствует студент первого курса Вергилио. Он старше меня, правда, но мы русскому языку их учим, иностранцев наших.
Ну да, проблема сложная. Все понимают, что английский – это международный научный язык. Хотим мы, не хотим.
Кофейку не отбью себе. Virgilio, can you hear us?
Yes, I'm preparing my speaker.
Okay.
YouTube идет с задержкой на минуту.
Да.
Добрый день.
Здравствуйте. Говорим с задержкой. Я вчера участвовал в общем собрании сибирского отделения. И на одном компьютере, как... Да-да. И вот на одном компьютере поставил Zoom, а на втором, у меня там большой экран, поставил YouTube. И когда выступал, что-то говорил, видел, как задержка происходит. Я даже в секундах отмерил эту задержку. YouTube идет. Пытался внукам объяснить, какие причины задержки. Вот как сигнал летает туда-сюда.
Ну, у нас в связи с онлайном культура соблюдения регламента повысилась. Как правило, все занятия начинаются минуты, ну, может быть, там.
Намного меньше причин для опоздания. Ни пробки уже. Ничто не может.
Omid Razizadeh is here. He will present in English our presentation.
Okay. Ну что, я думаю, начнем. Dear colleagues, дорогие коллеги, рад приветствовать вас на конференции, международной конференции, посвященной применению методов искусственного интеллекта в науках. I'm glad to see international speakers here. I'm also glad to present that we are opening the conference on applications of artificial intelligence method in sciences. И вступительное слово я предоставляю члену-корреспонденту Российской академии наук, главному научному сотруднику Института вычислительной математики и математической геофизики Сергею Юрьевичу Кабанихину.
Спасибо. Уважаемые коллеги, я два слова по-английски, потом буду, наверное, на русском. Dear colleagues, first of all, I would like to thank Professor Pavlovsky for the invitation to take part in this very interesting and important conference. Artificial intelligence is a very important part of, but rather heuristic and empirical part of the modern science. And if you look carefully on the papers and the program of your conference, about 90% are about neural networks, genetic algorithms, stochastic optimization. And I think that the most interesting part for the mathematicians, is the justification and estimation of the convergence of this technique. Если можно, я экран сейчас, на экране покажу презентацию.
Да, пожалуйста.
Так, слайд. Все ли видят, да?
Да, видно.
Коллеги, все понятно, спасибо. Я постараюсь коротко. Ну, во-первых, поздравляю всех, это очень важное событие. Евгений Павловский, по-моему, так героические усилия совершает вот, ликвидировать отставание, прямо скажем, в освоении этого широкого комплекса, который сейчас называется искусственный интеллект, применяется, развивается огромная армия ученых. Ну и, конечно, наш университет, Новосибирский и Сибирское отделение должны, обязаны догонять и тоже развивать. Хотя во многих областях новосибирские ученые являются лидерами. Вот. Одна из них – это обратные задачи. Мой доклад, хотя и короткий, но использует работы вот моих учеников, профессора Шишленина, доктор наук Ольга Криворучко, без 5 минут доктор наук, кандидаты Новиков, Зиськов и магистранты. Первого года Алексей Приходько, второго года Приходько, Прохошин, первого года магистрант, ну и вот бывшие магистранты и уже работающие во Франции некоторые и так далее. Значит, у нас есть два журнала. Сейчас это очень ценится, импакт-фактор и прочее. Поэтому я приглашаю участников, во-первых, вот международный журнал «Обратные некорректные задачи». Милости просим, даже труды можем в специальном выпуске издать. Ну, для математиков это достаточно высокого уровня журнал. И плюс Сибирский журнал вычислительной математики, который в Спрингере переводится Numerical Analysis and Applications. Тоже, хотя в основном русскоязычная коллегия, но очень высокого уровня. Здесь академики, члены-корреспонденты, профессора, широко известные в вычислительной математике. Так вот, Inverse Problems. Это область, сейчас она базируется, конечно, на классических дисциплинах математических, и алгебра, и анализ, геометрия, функциональный анализ. Я уже не говорю о матфизике, с этого все и начиналось. Оптимизация. Ну и вот слева и справа, конечно, это статистика. Вообще математическая статистика многими рассматривается как обратная задача теории вероятности. По наблюдениям нам надо восстановить характеристики. Ну, конечно, распознавание в Советском Союзе начиналось. Академик Журавлев, который сейчас возглавляет наши комитеты, и его ученики. Ну и уже выше стоит, конечно, и работа с большими данными, и машинное обучение. И я уж тут не пишу Artificial Intelligence, это понятно. Так вот, в чем основа обратных задач? Извините. Значит, самое главное, и вот здесь вы видите аналогию с задачами распознавания, искусственного интеллекта. Если мы запишем обратную задачу как некоторые операторные уравнения, то есть некоторые уравнения, которые неизвестны коэффициенты, параметры и так далее, переводит в данные, которые мы можем измерить. Тут традиционно задача называется корректной, если можно доказать, что для любой правой части решение существует, если это решение единственно в рассматриваемом пространстве. Ну и самое главное, непрерывно зависит от вариаций данных. К сожалению, в практических задачах и особенно в задачах искусственного интеллекта, как правило, не выполняется ни единственность, ни непрерывная зависимость. Немного изменим данные и можем любые другие решения получать тем же алгоритмом. Ну и вот задачи, в которых хотя бы одно из этих свойств классических не соблюдается, называются некорректными. Ill-posed. Вот. И наиболее интересные практические задачи и в обратные, и так же, как и в Artificial Intelligence, они, как правило, ill-posed, некорректны. И поэтому такой большой интерес у специалистов по обратным задачам, это новая область исследований, хотя новая, как правило, хорошо забытая старая. Еще Аристотель решил обратную задачу проективной геометрии. Он, наблюдая за тенью Луны, за тенью Земли на Луне, он пришел к выводу, что что-то круглое, раз у нас есть такой овал на Луне, и все понимали, что это тень Земли, значит, что-то круглое. Хотя была дискуссия. Были люди, которые считали, что это барабан Земля. Ну, на китах стоит барабан такой, он тень дает на Луне круглую, а вот в целом-то интуитивно, конечно, казалось, что Земля плоская. Что ж тут? Ну и вот эти дискуссии Аристотель завершил, привлекая, как и обычно в некорректных и в обратных задачах, априорную информацию. Какую? Во-первых, уже знали, что к центру тяжести тела падают. Поэтому он говорит, первый аргумент, если мы бросаем тело, оно ведь летит вертикально вниз, а не к барабану под углом, а всегда вертикально вниз. Второе, карта звездного неба. Уже понимали, что если мы путешествуем, то достаточно далеко, то звезды меняются. Это тоже был аргумент, что все-таки не барабан, а круглая Земля. И, ну, а если идти дальше, вглубь, то и Платон, в общем-то, формулировал и говорил об обратной задаче. Все, что мы видим и слышим, это только эхо и тени на стене пещеры. А там где-то в комнатах, где-то костер, но мы этого не видим. Мы решаем обратную задачу. Вот. И все эти связи, вот вы почитаете, презентация у вас останется. Так или иначе это возникает и в вычислительной алгебре, в дифференциальном интегральном исчислении, частных производных и так далее. Даже дифференцирование уже формулируется. Это, в общем-то, некорректная задача, потому что то, что мы измеряем, это точки. Можем интерполировать, но ошибки только в основном пространстве C непрерывных функций или в L2. И поэтому для того, чтобы как-то анализировать дифференцирование и исследовать приближение, необходим этот самый подход. Мы предполагаем, что решение существует гладкое, тогда можем оценить разницу между конечными разностями и истинной производной и так далее. Так. Ну вот, приложения понятно, и физика, и медицина. Начали в астрономии более-менее строго изучать. Хотя еще лорд Релей спрашивал в своем трактате по акустике, можно ли услышать плотность струны. Ответ оказался положительным, можно услышать по спектральным свойствам, можно восстановить плотность струны. Даже потом Кац известную лекцию прочитал, можно ли услышать форму барабана. Тогда барабаны – это из кожи, поэтому плотность можно. Даже форму нефтяного месторождения можно услышать. Ну, а вот если, давайте немного математики все-таки, это вот они, сколько сейчас можно обратных задач. Если вы умножите, то есть они классифицируются по типу операторов, эллиптические, параболические, интегродифференциальные и так далее. Дифференциальные уравнения по граничным условиям Дирихле, Ноймана, Робин, по информации, которая измеряется на границе, внутри области, кинематические данные, время прихода волны, спектральные данные, данные рассеяния и так далее. Ну и также по источникам. Что ищется? Иногда ищется источник, иногда граничные условия, иногда коэффициенты, а иногда и само уравнение. Значит, artificial intelligence, одна из целей, возможно, есть закономерность, которую можно выразить формулой. И так и делают. Часто выводят уравнения. Понимаете, вот оно оказывается сложным, интегродифференциальным, гиперболопараболическим, но оно описывает то, что происходит в непонятной нам среде. Плюс, конечно, по операторам и по областям. Поэтому, если вы вот это перемножите, вот эти вот точки, количество точек, вот и получится, сколько сейчас бывает обратных задач, исследуется и так далее. Но по некорректности тоже вот, диаграмма лучше всего отображает. Есть корректные задачи, существует решение и так далее. Потом, вот, если мы вот так пойдем по стрелке, против часовой стрелки, то увидим, то будем к некорректным приходить. Нормальные решения, псевдорешения, нормальные псевдорешения и так далее. До самых некорректных. Вот. Ну и, конечно, большинство задач вот, и оптимального управления, и обратные, ну и задачи обучения, они, как правило, сводятся к минимизации какой-либо целевой функции. Что-то надо минимизировать. Это естественно. Потому что, поэтому обычно надо приблизить, это вот идея Андрея Николаевича Тихонова. Он, правда, не в терминах NP-hard, а в терминах компактов, но это, в общем-то, об одном. Надо приблизить нерегулярную, некорректную, невыпуклую задачу, приблизить решать хорошую и сосредоточиться на оценке близости вот нашего приближения. Это называется регуляризацией. Вот. Ну и несколько слов здесь и о том, как это в оптимизации. Вот. Здесь я не буду, вы как раз это и будете обсуждать. Я только привел несколько примеров, несколько фраз на эту тему, потому что время у меня ограничено. И 2-3 примера. Вот сейчас эти самые сиеровские модели исследования эпидемии ковид. Фактически есть законы сохранения и скорость периода. Я самую простую говорю. Скорость изменения, значит, заболевших, инфицированных и восстановившихся, она зависит от произведения. Это классический подход еще из химической кинетики. Это понятно, что зависит от того, насколько они друг друга заражают или там, и так далее. Ну, вот эта система. Беда в том, что мы коэффициенты не знаем. Это обратная задача, прежде всего, должна быть решена, чтобы что-то сказать о развитии эпидемии. Ну вот, конечно, минимизируется функционал. Ну и, конечно, при таких вот сложных коэффициентов мы не знаем, и данных даже мы не знаем точно. Вы понимаете, что не все попадают в статистику. Кто-то заболевает, умирает от ковида, а кто-то от другого и так далее. Это сложно. Кто зарегистрирует, как тест работает, это все сложные проблемы. Мы их не касаемся, но тем не менее можно решать, и есть сценарии и так далее. Вот. И методы, конечно, вот локальные методы – это классика, и градиентные, НЛ-пирамида, регуляризация. Но сначала надо приблизиться к локально хотя бы глобальному минимуму. Для этого и существует simulating annealing, генетические, tensor train decomposition и так далее. Так, ну я вот на этом буду... Сколько у меня еще минут? Коллеги?
5 минут.
5 минут. Вот я и говорю, что, значит, вот задачу, конечно, сначала смотрят, что вообще мы можем определить из этой задачи. Это, кстати, очень, мне кажется, очень полезно. Identifiability. Можем мы определить параметры, которые нас интересуют, или нет? Вот в математике есть такие методы. Ну, конечно, sensitivity-based analysis, когда мы чувствительность модели измеряем, практическое идентифицируем, структурное. Это очень хорошие новые области математики. Ну и вот добралась теория обратной задачи и до social networks. Только пример. Вот данных довольно много, и Facebook, и Twitter, и Google, и у нас сети. И можно, оказывается, это описывается естественно системой уравнений диффузии, как данные распределяются. Ну, вот, и можно их анализировать, и градиент выписывать, и так далее. Это тоже широкий фронт работ. И там, когда мы уже близко к глобальному, НЛ-пирамида включаем, ну вот и эпидемия, и новости, они примерно по одним законам распределяются. Это я пропущу. Ну, конечно, вот эвристические методы наиболее эффективны при быстром подходе, хотя они нуждаются в анализе. Вот где-то мы их применяем смело. И это большие данные, поэтому, конечно, тензорное разложение необходимо. И иногда тензоры в обратных задачах, они не вмещаются в компьютер. Их надо приблизить, так же, как функцию полиномом, так и можно малоранговыми тензорами. Это тоже очень хорошая теория. Вот. Ну и дальше вот карты наши по России, это я уже модели, я это пропущу, но хотел бы вам все-таки порекомендовать оптимизацию, вот посмотреть и презентацию, и эти методы, поскольку вот эпидемия сейчас, на мой взгляд, является важнейшей проблемой для человечества. Потому что произойдет со всеми нами, со всеми нашими социальными институтами, включая университет, в итоге, в результате этой эпидемии, во-первых, когда она закончится, какие будут потери, и не только человеческие, но еще и интеллектуальные, и как психология изменится, это очень важные задачи. Мне кажется, на них сейчас необходимо сосредоточиться. Не то, что кажется, я уверен, это важнейшие задачи современности. Ну, я очень рад смотреть вот на программу вашу. Здесь много таких подходов, которые могут здесь сработать. Поэтому еще раз, уважаемые коллеги, большое спасибо за приглашение и за внимание. Я закончил.
Спасибо, Сергей Игоревич. Maybe some questions to Sergey Igorevich.
Здравствуйте, у меня есть вопрос. Денис Пономарев, НГУ. Сергей Игоревич, спасибо за интересный доклад. Я понял, что вам очень интересна тема применения методов искусственного интеллекта для решения задач вашей проблематики. Интересно ли вам движение в обратную сторону, применить ваши наработки для, например, ускорения методов машинного обучения в любом смысле, ну и так далее?
Да, спасибо за вопрос. Это очень важный для меня вопрос. Ну, буквально в точку вы попали, Денис, потому что мы регулярно каждую пятницу проводим международный семинар «Актуальные проблемы прикладной математики» и ежегодно школу, конференцию по некорректным задачам для студентов. Недавно она закончилась, больше 400 человек, мы так двигались с утра, с 9 утра до 9 вечера, начинали западное побережье США, Калифорния там и потом Китай, Япония, двигались через Байкал к Новосибирску, а потом Москва и Европа. С 9 до 9 14 дней. И, конечно, самое главное, как можно было бы применить методы. Вот тема сегодняшнего моего сообщения, это самое главное для нас является, потому что, ну, понимаете, как математики мы привыкли все-таки обосновывать наши методы. И здесь вот, ну, вы видели наверняка теоремы про генетический алгоритм. С определенной вероятностью, там пара страниц формулировка условий, а потом результат, ну, такой, в общем-то, неплохой, что с такой-то вот с такой-то вероятностью алгоритм находит глобальный минимум. И, конечно, мы хотим это применить. И вот в этих практических задачах, и в теории. И вот я упомянул семинар, у нас выступали вот по TensorTrain Иван Оселедец из Скалтеха, выдающийся молодой ученый, и выступали, вот сейчас мы собираемся нескольких еще молодых специалистов именно по этим методам. Pattern recognition и tensor decomposition и так далее. Да, конечно, мы пытаемся. Я им всем задавал вопрос, где и что можно. У меня сложилось впечатление, что во многих задачах искусственного интеллекта там вшиты эти обратные задачи, и там необходимо применять идеи регуляризации, поскольку они очень хорошо отлажены, начиная с 1963 года, когда Андрей Николаевич ввел всю эту проблематику. Они хорошо и они могут работать, помогать оценивать некоторые этапы. Вот.
Я больше скажу, что практически все задачи машинного обучения – это и есть обратные задачи. То есть задачи восстановления функции вот, в каком-то сложном встроенном пространстве.
Спасибо, Женя. Я для себя это воспринимаю как подарок и комплимент. И очень рад. Дай бог, если так и будет, то мы с удовольствием, мы открыты к общению. У нас очень много молодежи. Вот и у Максима Шишленина 10 студентов, и у Ольги Криворукой 10 и так далее. Они все начинают с классических обратных задач. Но заточены, конечно, и молодежь их не задержишь нигде. Как они могут? Им нужен интерес, живая жизнь. Поэтому... Конечно, они будут изучать и все, что вы сейчас вот будете рассказывать, обсуждать, будем смотреть. Единственное, что сейчас, единственная проблема в том, чтобы вот в данный момент, вот мне Ольга Криворучка звонит, например, я не отвечаю, сейчас буду отвечать, что очень трудно состыковать всех на одной площадке, но есть в этом и хорошая новость. Если все это будет выложено в интернете, все зайдут и посмотрят. Обязательно то, что им интересно. Я приглашаю на сайт нашей конференции, нашего семинара. Вы можете увидеть доклады. Вот на сайте математического центра МГУ есть семинар «Актуальные проблемы прикладной математики». Руководители академик Тайманов, Кабанихин, Шишленин и Миронов, член-корреспондент. Можете зайти и посмотреть все видео и даже презентации. Вот я думаю, это новая реальность, она очень хорошая. Плохо, что мы не видимся, не можем пожать друг другу руки, поговорить, но хорошо, что мы все можем узнать.
Сергей, спасибо. Я благодарю, что есть этот семинар, сам регулярно в нем участвую, был на докладе, когда докладывал Иван Оселедец. Видится очень важным, чтобы тот потенциал, который есть в математическом комьюнити, в Академгородке в целом, реализовывался и в области искусственного интеллекта, потому что потенциал действительно большой, но не всегда есть заинтересованность заниматься такими задачами. Было бы здорово, чтобы вот участие состоялось.
Спасибо, я согласен с вами полностью, это необходимо, особенно для молодежи.
Еще вопросы? Так, ну если у нас вопросов нет к Сергею Игоревичу, еще раз благодарим за открытие, за слово.
Успехов вам.
Спасибо. И сейчас я приглашаю выступить Александру Васильевичу Шапееву с докладом о методах машинного обучения в молекулярных исследованиях. I suggest for invited lecture from Alexander Shapeev, machine learning in molecular simulations. Please.
Thank you. Can you hear me and see the screen?
Yes.
Okay, thanks. So first of all, thanks a lot for this opportunity to speak to the audience of Novosibirsk Akademgorodok. Second, I want to congratulate everyone. I was happy to read the news that Novosibirsk State University was the second among the Russian universities shared with MIPT on the Times Higher Education rating. So this is very good news. I suggest you continue moving forward. I see potential that you can do even better. So today I will speak about largely what I'm doing on machine learning for molecular simulations. And there will be kind of two themes that I'll touch upon. One is data-driven modeling versus classical modeling. And classical modeling is something that I learned. So my next slide will be, let me see, yes. So I did my bachelor and master in mechanics in Novosibirsk State University. I'll move to the first slide. So Akademgorodok school is very good in classical modeling. All the data-driven modeling I already learned after I've left Akademgorodok, but there's interesting kind of opposition between the two. And I will speak a lot about questions of reliability. I will speak about that later. So this is my brief career. I finished my bachelor and master degree from the Faculty of Mathematics and Mechanics. My advisor was Vladislav Pukhnachev, so the diploma is in mechanics, and namely I was doing computational fluid mechanics. And then I did my PhD in Singapore. I came back and did PhD in mechanics from Novosibirsk State University. And then I went back and spent another 5 years abroad. And I was doing even more mathematics than I'm doing now. I did some numerical analysis. And from 2014, I'm working at Caltech, and I'm applying ideas of machine learning to interatomic interaction models, mostly for materials, although a lot can be applied for chemicals. Now I'm writing the ideas off because I'm not using core machine learning algorithms, but I'm trying to solve machine learning problems. So I'm not very particular about terminology of what I'm doing. Okay, so reliability is what I will talk about. Now, imagine you're trying to predict a material's property, for example, strength of material as a function of chemical composition. You mix different elements, you measure strength of an alloy, and you want a model that predicts the strength as a function of composition. Now, so I will consider a simple scenario when ground truth is known, when you can go and actually measure the strength. So if you're just interested in one data point, right? So you can just measure the error. There's nothing else you can say about the quality of the model. Now, if you have many data points, then you can measure the mean error and you can measure the maximal error, right? And they're not equal. And you can say, so this is typically the accuracy. When you read machine learning papers, mean absolute error is mostly what researchers write as their measure of accuracy. But there's also maximal error. And maximal error is related to reliability. And in materials modeling, so usually you are after a material with the best properties, a superconducting material at room temperature. Doesn't exist yet, but many people are trying to get it. And usually they're outliers, right? So if you train, there are probably many thousands of materials are known. If you apply machine learning algorithms to those, they will predict that superconducting temperature is 0. And this model will give you, it will be a very accurate model, and it will be useless because you're after an outlier. You want a really special material. So this is why reliability is important there. And I think in many applications of science, reliability is important. And again, so disclaimer, I disregard more complicated scenarios when ground truth is not known, right? This is a simplified picture. Now, molecular simulation tools are basically fall into these two classes. I'm speaking about classical simulation tools that existed before this big data hype has started. They're quantum mechanical models. They're reliable, they're accurate, and they're slow. They're slow because you need to resolve electronic structure. They're empirical, what's called force fields. When you disregard electrons, they're fast. It's just models that work with coordinates of the particles. They're not very accurate. They only give you qualitative accuracy, but both of them are reliable. And the reason why they are reliable is because we understand both models. And that's how classical modeling worked. It worked through our understanding of the model. We do not basically advance any model until we understand it. And now what's changed, now we build models on millions of data, and we don't fully understand those. And the question, so this is the important question, how to get reliability. So I will show that it's not too hard to combine this using data into an accurate and fast model. The biggest problem would be to make it reliable, this machine learning kind of models, okay? So let me continue why this is important is shown on this slide. So this is a typical pie chart of supercomputing time spent on different fields of knowledge. So this is taken from the top 20 supercomputer of the time when the statistics was taken. It was 2013-14, as far as I remember. And then density functional theory is a quantum mechanical model mostly used for materials, takes quarter of the total supercomputing time. And then with quantum chemistry, this is mostly modeling of molecules. Molecules are typically smaller and they take less time. And these are the accurate and slow models, right? And then molecular dynamics is this. It's about 10% of total supercomputing time. This is the reliable and the not so accurate but fast models. So altogether, it's almost 40% of total supercomputing time is used in molecular modeling, and there's a lot of potential what you can do. So this slide shows what does it mean, fast and slow. So density functional theory, this is the accurate model. A typical calculation, you can simulate picoseconds of time of the system. It's about a few thousands of vibrations of atom around the equilibria and few hundreds of atoms. That's all you can do with accurate quantum mechanics, but with classical, you can simulate nanoseconds of simulation time and billions of atoms. Again, the challenge is to make models as fast as this, but as accurate as this. And both of them are reliable, and that's what machine learning models also should be. Now, I like this example, reading the book of Richard Feynman. Machine learning models, it's a very new field, and there is a lot of, I mean, whatever we're doing now, we don't know how to make things really reliable. We build accurate models, but sometimes the models are not very useful. But this is an example from quantum mechanics. When in early days, people were working on something that was also kind of useless, didn't go anywhere. And this is the quote from Richard Feynman. So he was giving a talk in the seminar, and then he was discussing it with Pauli, and the talk was about quantum theory of gravity, which has never developed even to this point, but he was working with his supervisor. And then he said, my supervisor never solved it. And the quote says, I never solved it either. A quantum theory of half advanced, half retarded potentials, and I worked on it for years. Right now, quantum mechanics is a very reliable field. It's probably the most accurate, or one of the most accurate theories that we have now, but in early days, it was not exactly that. So I believe maybe in 10, 20 years, we will understand better how to do reliable data-driven models. Now, so this is the quantum mechanics that is used for materials, right? So the quantum mechanics for materials, this is the simulation that you want to conduct. There are ions, right? These are nuclei of atoms, and there's electrons around. And then you start with the Schrödinger equation, you apply the Born-Oppenheimer approximation that allows you to treat those nuclei as classical particles. And then you want to do the Kohn-Sham approximation. The Kohn-Sham approximation derives the quantum mechanical energy of interaction as the function of electron density. And the assumptions that are made is this. So this energy is written as an easy quantum mechanical part of an electron not interacting with anyone else. A wrong classical part is if electrons are classical particles interacting with each other, which would be totally wrong. And then they do quantum corrections for free electron gas. Free electron gas means like there were no nuclei, just a box and electrons. And I think it would have been crazy back in 1965 where they proposed this. I can imagine in the seminars, they could be viciously attacked by researchers saying it's complete nonsense. But it turned out that it's a really good model. It's almost by luck. In 1998, this model got a Nobel Prize. So Kohn, together with another person who developed a software to compute it, two of them got the Nobel Prize for this. So it turned out to be a very accurate and reliable model. And again, the problem is, this is already a practical problem. It's not their problem that it is slow, right? So it's accurate, reliable, and slow. And the reason why it is slow is because still the dependence on electronic degrees of freedom is hard. And to make it fast, we need to get rid of electrons. We want a simple model that has only atom positions and nothing else. And this is the way to make those models fast. And one of the most successful early attempts to do this for materials was by Michael Baskis. He worked in Los Alamos at that time. And this was his idea. So this is his 3 most cited papers, and this is the first one. And he and his colleague was studying hydrogen embrittlement. So there was a metal, and there were hydrogen atoms inside the metal, and they wanted to simulate it. And they said the following thing. They said, hydrogen embedded in metal, let's just model it as hydrogen embedded in electron gas. Let's forget about the metallic atoms. Let's just look at the electron gas. And this was a very reasonable physical assumptions. They managed to publish it in a top physics journal. And then they had an idea, okay, but so everyone wanted to simulate metals. And then they said, if hydrogen embedded in a metal is the same as hydrogen is embedded in electron gas, why don't just metal atoms, we consider them as those embedded in electron gas? They quickly found they cannot get accurate results with this, but if they relax some parameters, they say, let's just fix the functional form and find some 3 parameters from data. And it turned out to be a very accurate model for those times. It was 35 years ago, right? And by far, this was the most highly cited papers, and I think the total number of users at least 10 times more. Many people just stopped citing the paper and used their method. Okay, so this is how it looks. So there are atoms that we want to find their energy. So after we find the energy of interaction, we can find the gradients, and they will give us forces. So we can run molecular dynamics, find energy minima, whatever we want. And the functional form is this. So each atom depends on the atomic environment of itself, and its energy is some embedding function. This is the energy of an electron gas, and whose density is given by some empirical functions, which you cannot get directly, but they feed from experimental data. And early potentials 35 years ago, they just had three parameters, and they were fitted from 10 experimental data. And it was very successful. And what's different now is that over a weekend, I can generate hundreds of thousands of quantum mechanical data. And now I want to incorporate all those accurate data into these functions. And that's how machine learning potentials came about. So wrapping up the overview, so we have those classical models, the quantum mechanical model and empirical models, and we are developing data-driven models. They're pretty new, they're 10 years old. And so empirical models, they are reliable because of simple functional form that we understand. Quantum mechanical, they're reliable also because we understand it through asymptotics, symmetries, and so on. And the challenge is how to make reliable data-driven models, because we don't understand the functions we fit a lot of data. Right, and then we'll get accurate because we use lots of quantum mechanical data in the data-driven models, and fast because our models look more like force fields. We don't have electrons. So this is the challenge that I've been working with, and now I'll show you a little more concrete stuff on what I was doing. Right, so a very simple picture, probably too simple for this audience, is that I like to think of machine learning as an interpolation in a very high dimension. And so this problem, if you had just a simple water molecule, you can parameterize it with 3 degrees of freedom. And if you have a quantum mechanical model that calculates the electronic bonds between the atoms, you can just compute it on a 3-dimensional grid, interpolate, and you're done. You don't need machine learning algorithms. The problem is when you have hundreds of thousands of atoms. I will actually show how to do, but yeah, the idea is this. So you choose a machine learning model. It could be neural networks. I actually choose linear regression with the special basis function. I find it works best. I will show you. And then we generate lots of data, lots of atomic configurations, compute energies, compute quantum mechanical forces, and we minimize the difference on data. Next, I will show you, so this is basically the overview of my talk. I will show you these models. I will show how active learning algorithms ensure reliability of those models. And then I will quickly show you some applications. Right, so the philosophy of doing this is the following. So unlike those empirical models that are based on our understanding, we do the following thing. So we use principles of physics that we're sure about. So we use locality. We know that the interaction is not exactly local. It's just the interaction decays, but we have to, and we can use it. And then we use physical symmetries. Permutation of equivalent atoms. We use rotation inversion symmetry. And then translational symmetry we get for free if we parameterize it with relative distances. And then we don't make any other assumptions that we aren't sure about. Unlike classical modeling, but instead we try to get sufficient data to get everything else about our model from the data. Okay, so this is my version of those potentials. So the first thing you need to do is you need to find the right descriptors of atomic environments that satisfy the symmetry. So use these moments of inertia of surrounding atoms. So the formula is here. So what I do, I have central atom I, and then I sum over the neighboring atoms, and then I apply, so this is the radial term. It's a simple scalar function applied to interatomic distance. And then if we forget about the second part, what I'm doing, I'm taking different shells of atoms around this atom, like rings on this picture. And this is responsible, so this part is responsible to taking kind of different rings of atoms, and that would not be enough because rings would rotate and we need to fill it. So we take angular part here. And the angular part, if we multiply it by this Rij vector, then this is a vectorial quantity and it gives us the center of mass relative to the position I. If we take a product of two Rij outer product with Rj, we get a matrix quantity and we find that these are second moments of inertia that I learned in physics class back when I was studying at school. And if we continue and taking higher order moments of inertia, I prove that these are actually the complete description of any possible local environments. And what I later do, I compose basis functions that are different contractions of those inertia tensor to a scalar. So I there's infinitely many ways to do it. I take finite number of basis functions, and then so my potential is a linear combination of these basis functions. I'm a mathematician by training, so I prove that this is a complete basis. You can expand any local function in this basis, and it actually works exactly how it should. So if I increase the number of basis functions, my error also decreases. I can only prove that I have an algebraic decay, right? It's number of basis functions to some power, and the power actually depends on how different my configurations are. It can be large and can be small. And I like a lot the work that I was a part of that was done in University of California. So they compared my potentials, which are blue diamonds, with other existing potentials. And my potentials had a better, slightly better accuracy to computational cost balance than other potentials. So the red ones are neural networks based potentials, and they're slightly slower and they actually need more data. So to get them converge better, they need much more data. And there are other potentials. These are Gaussian process potentials, and they're slow because you need to take a lot of kernels to make them accurate. That's probably all I wanted to show. And the third part is active learning. Now, the story about active learning is this. So if I go back to this slide, right? So this slide is about error and computational cost. And this is something I was trained to look at as a mathematician. I started in Academic Городок with computational methods, and they're all about error, and they're all about computational cost, inverting matrices and this kind of stuff. And excuse me. So I was very happy about it, but then I learned that reliability is actually a bigger issue than accuracy or computational cost. And this is how we solve the reliability with active learning. So we have a molecular simulation. You can think of molecular dynamics. So it generates a molecular configuration, and it needs forces to make a time step. And before actually predicting energies and forces, an active learning algorithm decides whether this configuration needs learning or not. And if yes, then we get a quantum mechanical data and retrain a potential. Otherwise, we predict it directly. And this is the critical thing that ensures reliability in practical simulations. So this is how one can motivate it. So here I play a game that my blue function, which is just arctangent x, is the true quantum mechanical energy, and I put 20 random points on an interval from -3 to 3, and I do a fit with the piecewise, with a linear, with an affine function, right? A polynomial of degree 1 and polynomial of degree 5. So interpolation of the linear function is not so good, but extrapolation is not so bad. And often this is enough for molecular simulations. So I take higher number of parameters, my interpolation becomes better, but extrapolation becomes worse. And this is an issue that needs to be done. And here's what active learning can do. So imagine we have an algorithm that tells for every point we're trying to fit with, whether it needs to be added to the training set. So if I take polynomial of degree 5 with 6 parameters, it takes first 6 functions. And then the way I conduct it is when I'm adding points, I'm sacrificing some of the existing points so that I always had 6 active points in the training. So I call it active set, I learn in all. So next point will be added here. So I add this and some points here leaves the training set, and I continue until points will appear somewhere where I feel I have a sufficiently good approximation. So I go on until I start extrapolating, and then I switch on learning until I cover the region well. This is roughly how it works. So I use de-optimality technique from machine learning, actually slightly modified. If you're going to have questions, I'll try to finish earlier. And if you want to see mathematical details, I will be able to present. But otherwise, you can think of me doing a convex hull, right? So I have my basis functions are descriptors, and my active set is a convex hull around those. And whether the point gets inside or outside, I say it's an interpolation or an extrapolation. Except that in many dimensions, we know that in 100 dimensions, any point inside will be pretty far away from any point on the boundary. But the thing is that I have a linear model, and the convex hull becomes a simplex there. And if you do math, you realize that this problem is actually solved in the right picture with many dimension and simplex rather than 2 dimensions and convex hull. Okay, so coming to the last part of my talk, I will show you some of the applications that we managed to do with this. The first one, it's a prototypical application. I call it application number 0. We run molecular dynamics. So there are 100 atoms in a box, and at the room temperature, they vibrate. And I want to know the forces from quantum mechanics. So this is the number of molecular dynamic time steps versus the number of quantum mechanical calculations. Quantum mechanical calculations are expensive. They're typically minutes to hours per time step. So these are many days of calculation if we do a calculation every time step. But if we switch on active learning, then after an initial stage, we kind of learned everything, and we stop learning, and our total quantum mechanical calculation is limited by something between 500 or 1000. Now, the difference between the curves is the parameter, we call it threshold. It's a parameter that controls how much extrapolation we allow, right? So, and it's good to allow, this a dimensionless parameter, it's geometric parameters. So somewhere between 1 and 10 is almost a universal number for the systems. If we look at the error, this is electron volts per atom, then the difference between 1 and 10 is not significant. So 0 means we don't allow any extrapolation, and we still have an error. And this is what I would call it as a mathematician, a model error. We choose 100 basis functions, and we get this error, and then this is the sampling error. We do not train on all configurations. We train only on a limited number of configurations, and we get a little bit of extra error. And in theory, we can control both. in practice, non-locality gives me some lower bound on the error, which we're often hitting. Okay, now a more practical application. So I'll try to finish maybe in 10 minutes to give 15 minutes of questions. A practical application, so these are what I call zero temperature phase diagrams, or it's called Maxwell construction of convex hull of stable structures. So this is an aluminum nickel titanium system, and every point here is a stable structure. And if you hit inside the triangle and mix those elements and cool them down, what you see in reality is grains with this composition and this composition and this composition. Okay, it splits into different structures. So the way it's done in practice, if you want to do it computationally, not experimentally, is you take 1.5 thousand candidates for those structures, very well chosen, and then you equilibrate them on density functional theory. So this is the structural relaxation part with quantum mechanics. And relaxation, it generates configuration. It needs energies, forces, and stresses to do the gradient descent and find the local minimum of energy. So this is the pictorial view. So this is the prototype structure. It's a candidate structure for a given alloy. And then you minimize the energy. So you do local minimization. It may turn into a different structure with a local minimum of somewhere here, minus 0.09. And then you put this on the plot where you have composition versus energy. And then you put those 1.5 thousand structures here, and you take the lower convex hull, and these are the structures that you predict that you find in reality when you make those alloys. And what we do now, so this step we do with active learning, machine learning potentials, right? So most of the times, this is our model that predicts energies and forces based on configurations, and sometimes we automatically train it with quantum mechanical data. And now we can do it on a much bigger set of crystal prototypes because we're much faster. So just for the information of organizers, yeah, so my Telegram is on my phone. So if you need to send me a message, I will see it. Right, so, and in practice, this is how it looked. So we start with 400,000 structures, and we do two things at once with active learning. We find all 400,000 local minima and put them on the phase diagram, and we train our potential with active learning. We get a relatively large error. Well, you have to maybe believe me that it's large error. And we can stop here and say, okay, we get some, our phase diagram with a little bit of numerical error, but we can continue and say, it's just a screening tool, right? We get 40,000 structures that are close to this energy minima and repeat the procedure. Now, because they are much closer to the minima, it's a smaller set of structures. The next time we do it, we have a much smaller error. And this is already enough for most of applications, but we can continue and we can again select all now more accurately the low energy structures and do the final structure, the relaxation on DFT, on density functional theory with quantum mechanics. Now, this way we find some topologically new structures that were not in the training set, which we would not be able to find if we do passive machine learning. And these are the results for this application. So if we do the final step, there's no approximation error in the answer. There's only a risk of missing a structure in the interval of 4 sigma for the energies. And this is something that we control. We get 100 times speed up. And the 90% of the time is the final step of doing pure quantum mechanical calculations. Sometimes we don't need that, and if we are okay with a small error, then it will be 1,000 times speed up. And again, the calculation of the training set on quantum mechanics is the most time-consuming error. So this is what machine learning potential gives me. And we also find new structures that were not discovered computationally with this, because we can do it much better and we can screen many more structures. Okay, so less detailed, a few more applications. So we can do molecular dynamic simulations at high temperature. So we study elastic properties directly from quantum mechanics of, this is pure titanium, but now we're doing alloys. And again, so we trade a statistical error of quantum mechanics to a model error and 100 times speed up. So this is what machine learning gives us. And there's no statistical error because they're much faster and we can collect all the statistics we want. So with colleagues, so now we're working with colleagues from the Ross Atom Institute. We study diffusion for the defects. And again, we can see these events of diffusion of defects also from quantum mechanics and automatic learning. Molecular reaction rates, we also compute with this procedure. Phase diagrams is what we are lately doing. So here we get a melting curve of the silver palladium system, again, directly from quantum mechanics with machine learning potentials. A bit more details on this. So this is recent work where we study thermal conductivity of two-dimensional materials. So here on the bottom is, this is graphene, the famous two-dimensional material, and this is boron. It's a two-dimensional material based on boron, and we take different grain boundaries between those, and we calculate from quantum mechanics the thermal conductivity of all those, and then we can do a finite element simulation of thermal conductivity of different grains of those, and do basically this multi-scale modeling from quantum mechanics all the way to real, basically millimeter and meter scale. And this is really last application. So this goes beyond machine learning potentials. There's a lot of other applications of machine learning for material modeling. One is direct property prediction, but what I want to show is phase diagrams. So you can run molecular dynamics on, and on this plot, every point here is a molecular dynamic simulation. So you can set your density, you can set the temperature of your simulation. You can run molecular dynamics, and molecular dynamics gives you data from which you can tell that this is fluid here, this will be gas, this will be liquid, this will be solid. Between this, it will be coexistence. And the way it works is this. It's also a very good problem for machine learning. So every line here is the result of molecular dynamic simulation. So you fix temperature and volume, can fix number of atoms and fix some other parameters, and you get data. You get enthalpy and pressure of the simulation with some error. And we are applying Bayesian machine learning. We're applying Gaussian processes that can actually be aware, they can take as input errors. And they can predict free energies of the phase at different volumes and temperatures. We can take extrapolation to infinite number of atoms with error. So we can kind of construct those phase diagrams with error bars, which has not been done before, but machine learning algorithms allow you to do that. And another cool thing that machine learning algorithms allow, they can actually do adaptive sampling. So with Bayesian sampling, we can look at error of predicting a property, and we can define, I like to call it an information function. So the information function tells me that the next calculation that I need to do is here. It will decrease the error by the biggest factor. And then if I do a simulation, my error will decrease in some quantity. It could be this triple point on the phase diagram. And then my information function will change. I will see that now I'm much more accurate, and then it will say, okay, next point will be here. So I can do optimal sampling, or people say optimal experiment design when I conduct this. It's also an opportunity that machine learning algorithms give us. Okay, so I'm back to conclusion. I made the slide for the rigorous scientific audience that I'm presenting for. This is my second last slide. So the classical models are either slow or inaccurate. In many applications, they're not. Like finite element method can be applied to simple models. You don't need to machine learn a lot there. But classical models for molecular simulation, they're either slow or inaccurate, and machine learning models can be both fast and accurate, right? And then active learning and other machine learning algorithms can make it reliable. And these two actually make a breakthrough. They open possibility to do many applications that were not available. So it's this point, and there's also other opportunities to compute higher level properties. So for phase diagrams, we need to deduce the free energy, and they can also be done from machine learning. I will skip, I guess. Yes, there's some slides. I will quickly finish. Make my promise that this was not the last slide. Not vibrate, but they're chemically complex. They're so-called the class high entropy alloys. You can also do a bit. So for example, for a certain class of high entropy alloys, we applied all the tools and we predicted that, unlike it was believed, that they're stable up to room temperature. And this is corresponding to experiments, because in experiments, they never saw any phase transition when they mix it. And now we managed to explain why. Okay, so this is really my last slide. So the code that we do most of the things is available. And now we have a pretty good documentation here. So this is the website where you can download the code. You need to register and agree on the terms. There's documentation, there's a paper, there's a tutorial that teaches you to train them. And most of the things that I showed to you today, you can repeat by yourself if you're interested. So I will go back to the slide with conclusions to stimulate questions, and I'm done. I thank all of you for attention and opportunity to speak. I'll be happy to take questions.
Thank you, Alexander, for such a great presentation. Yeah, we have questions. While other thing I cannot ask, have you heard about Fermi-Net's approach from DeepMind for molecular modeling, for quantum mechanic modeling?
Well, I know about the works. So sorry, which group you said? Oh, DeepMind, it's Google, right? Google. Yeah, I know
yes.
about Google Google results. I forgot how they call it. Yeah, I think they apply it mostly for molecules. There's another big community that almost do not intersect. One applied for materials, the other applied for molecules. Yes, I know, I believe they are based on some ideas of convolutional neural networks, and they work pretty well for molecules. And I did not see, I saw one attempt to apply it to materials, and it was not that good. I would say, just to one comment, so my problem, I'm fine with using neural networks. So once they will have one thing that is missing that I will name, I will be happy to stop doing what I'm doing and start doing neural networks. The reason why I'm not doing neural networks is because active learning algorithms are not very reliable for neural networks. So they are, I can tell more about this if you want, but basically you can show that you can reduce error, you can sample better, you can collect the training set more efficiently. But if I go back to my very first application, let me just flip those slides. Right, so what I need to do is I need to relax 100,000 structures with 100% reliability. Now, if you think about this, so structure relaxation is, with little bit of exaggeration, I can say that this is an adversarial attack on a model, right? So I say, this is my model, and then I have 400,000 attempts to find the minimum of the energy. And if you don't cover your space very well, you will find those points that are not fitted well, and you will go into unphysical minimum of the energy. And if at least one structure will not be relaxed properly, then users of this will say, no, maybe I should use more reliable algorithms. So this is the problem with neural networks. So such algorithms do not yet exist. So I saw like results that they active learning can help, I don't know, reduce the number of successful adversarial attacks by a factor of 10. I saw it maybe a few years ago, maybe now it's better, but I almost need 100% reliability. Anyway, I already answered your question and a couple of my questions. So
okay, yeah, we have 2 more questions. And like Denise, first time, Denise, please.
Thank you. Hi, Alexander. Could you please get back to the slide with the scenario of active learning?
Scenario of active learning. So let me try to get this.
Yeah, that's this one. I think I missed it. I really didn't get how you decide how to switch between classical modeling and machine learning. Could you please comment on that?
Sure. So what I need to do is this, right? The basic problem. So I have a molecular simulation. It could be molecular dynamics. It could be a local energy minimization. And what it needs, if you just look here, it generates different molecular configurations and it wants the energy and it wants the gradients of the energy to do the gradient descent or update the position based on forces. And inside, what I need to do is to make sure I can reliably predict. I need to answer this question basically. Can I reliably predict the energy and forces of this configuration without doing quantum mechanics, because this is very expensive. And so this is basically this is Dennis's question, how to do it, right? So the first thing is to say, so I have basis functions. I have linear model, and my basis functions, you can think of them as descriptors. So every configuration is a point in a 100-dimensional space. And then I need some geometric criterion based on existing points in the space and a new point. So if the existing point is, if the new point is inside, I say it's interpolation. I do not need new data. If the point is here, I say, oh, it's an extrapolation. I would need to take the point, the quantum mechanical calculation here. Now, since you ask, I'll try to find those hidden slides. Yes, they're here. I hope you can see them. Yeah, so this is based on ideas of de-optimality. I slightly changed them, but basically, let me do the laser pointer again. So my model is linear. So I have configurations, I have linear basis functions, and I'm kind of solving an overdetermined system, right? Where these are my quantum mechanical energies and theta are parameters that I want to find. So it has a tall matrix with number of equations that arose much more than the number of columns, which are basis functions. And then some will notice that I'm affected by my colleague, whose name was already mentioned today, Ivan Oselidis. I find an n by n submatrix with a Maxwell algorithm that maximizes the determinant. So de-optimality says maximizing the determinant is good. And so I need to select rows, and selecting rows are configurations. So the criterion says those set of configurations are good for training that maximize this determinant. And in practice, I already have my training set or active set. I get a new configuration, and I define the extrapolation grade is by factor by which determinant may increase. And if it's less than 1, it's an interpolation. If it's more than 1 plus epsilon, it's an extrapolation. And if I have those mathematical slides, I can show this. So if I do a little bit of linear algebra, I will show that the energy of the new configuration, if I try to predict, it's a linear combination of the energies in the training set with the coefficients that are directly related to my extrapolation grade. So if my extrapolation grade is less than 1, all these coefficients are less than 1 by absolute value. And this is why I call it an interpolation. If the extrapolation grade, so maximum of these coefficients is exactly the extrapolation grade. So when I keep extrapolation grade small, I ensure that I take linear combination with small coefficients. So it's kind of an interpolation. Okay, so this is a relatively quick answer with a little bit of details on how I do it. So basically, just to summarize, I compute the extrapolation grade and determinant of A. You can think of it as a volume of a simplex in this multidimensional space, and I'm trying to grow it. So I kind of take all the configurations that lie on the boundary in my 100-dimensional space of basis functions.
Okay, so does it really matter what kind of learning model you use here?
So here, I showed it for a linear model. It works for nonlinear models too. We're actually using nonlinear models for multi-component, but I believe that it works well when we are at the local minima for our parameters. So it wouldn't work for neural networks because in neural networks, we always do some early stopping. So we'll never go to really the minimum of our loss function. But here I go to the minimum of loss function, and then I can linearize there. I can take a kind of tangential manifold, and I can locally linearize the model there. Once I do it, I can use this machinery for those. So yes, I would say, yeah, the class of models is larger than linear models, but not applicable to neural networks. At least I don't want to try, and I did not know any good attempts to apply it for neural networks.
Yeah, I see. Thanks.
Okay, and the question, Petr, please.
Petr, I don't hear you, unfortunately, although your microphone is unmuted. Maybe you muted your microphone somewhere else. Oh, I still do not hear you. Sorry, we still do not hear you. Sorry, we still do not hear you. It's probably
yes. Yes, you may write now, like in chat.
Yeah, maybe. Yeah, would be good.
So, like while Petr writing in chat, small question: have you employed, considered an idea of quantum computations for your modeling?
I thought about this. So first of all, I think, I believe that quantum computation will start being useful after most of my career will be finished. So I'm not practically seriously thinking about using quantum computation. I respect the work some of my colleagues are trying to advance quantum computation, but they're mostly developing quantum computation algorithms. But probably at some point they will become useful. I'm not 100% sure they will ever be in the foreseeable future. But I would say basically there are two parts where quantum computation can be applicable. So one for doing, maybe show some diagram. So one is at this part, just do quantum mechanical calculations to collect data faster. And nothing I'm doing would change in this case, right? And second is for training the models, right? If you can optimize the machine learning model better with quantum calculations, how would you do that? There are attempts in particular for neural networks. For me, probably they will not be too useful, right? So if that will come to existence tomorrow, I'll probably start doing, okay, I need to do something more useful now than what I'm doing. But so far, they're far away from being practical, so I'm not worried too much. And I'm not really seriously thinking of using them in practice.
Okay, okay, I understand. So a question from Petr is, you may see...
Let me read it. I can read the question from Petr. As I understand, the method described did not concern for radiative transfer events. And is it hard to model the material's dynamics in case of radiative transfer? So Petr, I'm not a physicist. You probably need to explain what you mean by radiative transfer. I can imagine two different things. I will start answering the question, but maybe if you can tell photon absorption. Okay. Got it. Yeah. So photon absorption is, well, you need to start over. So all I'm doing, I'm assuming, I'm making one central assumption that the electronic degrees of freedom are in the ground state. If I go to the very, very beginning of my presentation, I had a tiny formula there. Yes, this is the key formula that maybe many missed. So I say that the energy of interaction of atoms is the quantum mechanical energy where electrons are in the ground state. And this is the central assumption that I'm doing. Now, if you have photon absorption, for example, it probably answers this question already, but I'll just say a few words, right? So photon absorption or other kind of events, once you absorb a photon, your electronic structure, it stops being a ground state, it becomes an excited state. And then depends, so then it will change the dynamics, will not so much change the dynamics of a material, but molecules, yes. So I know some people are trying to study exactly this, develop molecules for whatever photon detection materials or molecules. You need to start over. You need to say, no, now there's really many excited states, and then you need to see, are they stable, are they not? You may need to feed different potentials or do something completely different from the beginning. So short answer is no. You need to start over. Use ideas, but yeah, do it from scratch.
Okay. Not
yeah.
satisfied with answer. Yeah.
I'm glad.
So yeah, thanks again, Alexander, for answering questions, for giving such fruitful and presentation showing how we can benefit with machine learning methods in material science.
Yeah, thanks again for listening and thanks for inviting.
Great, thanks. So now we have, let me show our program. Our program is now like that we have a break, and after break there's this planet, the report from a report about selectivity verification, high dimensional dependence models, but at the moment I have not received any confirmation from participants, and unfortunately, like I just got to know that one of the authors, it's Vadim Moto, have died yesterday, and like so that was a very powerful machine learning specialist, and he was working for Russian Academy of Sciences. And so I suggest to take a break. Then we'll listen to the next report from Omid Razizadeh and Sergey Yakovenko about turbulence models and employing convolutional neural network to enhance turbulence models for channel flows. So let's have a 5-minute break. Okay, dear colleagues, let us proceed. Our next speaker is Omid Razizadeh, and he will present the report on the implementation of convolutional neural network to enhance turbulence models for channel flows, jointly with Sergey Nikolaevich Yakovenko.
Okay.
Yeah, so we'll let me additionally say that we have 20 minutes for the report and including the questions. So please give time for listeners to have to ask questions during that time.
Okay. Can you hear me?
Yes.
Okay. And you can see the screen.
Yes, we can see.
Okay. Hello, everyone. I want to talk about the implementation of convolution of neural network to enhance turbulence models for channel flows. This is the main topic of was my main topic of my master thesis with Professor Yakovenko. So first of all, let's see what is turbulence. Turbulence is the chaotic change in pressure and velocity. This is in contrast to laminar flows. As you can see from the picture, we can see the chaotic behavior, and we have different regions: laminar regions, transition, and turbulent boundary region. My research is based on this region, turbulent region. There are some equations for any fluid, in particular incompressible fluid, Navier-Stokes equation and the continuity equation. Navier-Stokes equations, we cannot solve them directly at high Reynolds number. And what Reynolds number means? Reynolds number means velocity divided by viscosity and multiplied by the length. This length depends on the definition of how we define it in different data sets. We have a direct numerical simulation, which means that we directly solve the Navier-Stokes equation, which is really expensive computationally and time consuming. And we have, which is accurate. It's not a model, we directly solve it, but we can do some assumption and mathematically do some mathematical assumptions with and have a model which is called Navier-Stokes, which we average over time. We cannot get the accurate prediction based on different ways, RANS, LES, hybrid RANS, LES. All of them are models. They are not accurate compared to DNS. This is a scheme of how this pyramid looks like. If we go up, the accuracy increase, but at the same time, the computational cost also increased drastically. For example, for complicated geometries and flow cases, probably direct numerical simulation cannot be achieved at all, even with supercomputer. It's not logical. So why we need ML? As I said, because we did some mathematical assumptions with it. So these are the models, and there is a discrepancy from high fidelity computations, which have which is the area of my research. And this is the key importance to reduce the model uncertainty. There are some formulations that I will talk in my presentation. First of all is shear Reynolds stress, which is this one, which has this formula. And another one is anisotropy tensor. And here I tensor by divided by 2K. This is the main thing that I'm going to do. I want to predict this BIG tensor. There are some, there's also another function, tensor function and scale invariance that some researchers did for input features. This is 10 tensors. The left part is tensors, and the right part is 5 scalars. And usually researchers, other researchers input tensor functions and scalar invariant, and some of them believe that only by inputting only 3 or 4 tensors and 2 scalar invariants, it is enough to have a good prediction and decrease the discrepancy. There are some researchers that did some research on this topic to enhance turbulence models. They use gene expression programming implemented by Vedrit and Sandberg, a research group. Another one is field inversion machine learning. And the first two are symbolic approach, which means that this is the area of this kind of research, the interest of CFD community, and the tensor basis neural network and physics informed machine learning. They are considered as black box. I would like to explain the first two, gene expression programming by Vedrit and Sandberg. They implemented it on different flow cases, jets, fakes, periodicals, converging diverging channel, and etc. It has two variants, frozen approach and CFD driven approach. Frozen approach is based on high fidelity data, which means that they train the model, they train the GEP model in an unsupervised manner, and they get some mathematical expressions and they insert it into the solver. Another one is that, for example, sometimes we don't have enough information in the data set to form these functions. For example, a strain tensor or rotation tensor, we don't have enough information in the high fidelity data set, which is DNS, or sometimes we consider also LES as high fidelity. So this is the area that's why this approach comes. This is based on low fidelity data to decrease the discrepancy between high fidelity data by defining a specific cost function. These two, as I said, we can insert them into a CFD code and check the applicability for other flow cases. For example, we trained the model on periodicals, we get some equations, we insert it into the CFD solver and run the solver for converging diverging channel, for example. The flow cases should be similar. They cannot be too different. Otherwise, the result won't be good. And this is the framework for frozen approach. I just want to show that to have some ideas. We extracted strain tensor and rotation tensor. As I said, some researchers believe that the first 3 tensor functions and 2 scalars are enough. They insert it into the model and they get some equations, and they insert it into the CFD code and run the solver. Another approach is field inversion and machine learning, proposed by another research group. This is also they can have symbolic equations and insert it into CFT code. They what did they do? They insert a corrective term into the RANS equations. Then they have an optimization task by J, and they insert it into the CFT solver, and each flow field they will get each flow field one by one, and they then they insert the simulation into the machine learning model by features like that I said, tensor functions, and they get the result. I just started this research, so as the first step, I wanted to try neural networks. This is the scheme of the convolutional neural networks that I used. And the methodology that I did, I used ANSYS ICM for meshing and OpenFOAM for running the solver. I extracted the point from the high fidelity dataset. I imported ANSYS ICM. I meshed the boundary conditions. Boundary conditions should be consistent. I interpolate the high fidelity data on low fidelity data, and use high fidelity data for training the convolutional neural network, and use low fidelity data for prediction, and I compare the results. The reason that I choose ANSYS ICM because the mesh, the geometry should be exactly the same, then the result could be better to compare it. So probably with OpenFOAM it is also possible. Some tools like Snappy Hexamesh. And this is the CNN architecture. These 131 and 150 is the cell number of cells in different direction, X and Y. And this is the 4-layer convolutional network. And I did the simulation for 3 flow cases. Converging diverging channel at Reynolds number 12600, periodic hills at 10,595, the square duck at 10,320, and this is just a picture of the mesh. And this is the some of the flow fields that this is for DNS. This is high fidelity data. We want our result to be like this. This is the ideal case. The left one is velocity in horizontal velocity. This is the you can see the vortex shedding, complicated vortex shedding. The RANS model cannot catch these. So if we run the simulation with RANS solver, we cannot see these this behavior. And this is the kinetic energy. You can see near the wall it is maximum, and when we go far from the wall, it decreases. The same for velocity and turbulent kinetic energy for periodic hills. Again, this is the high fidelity data. This is the left one is velocity, and the right one is the kinetic energy. So what I want to do, I want to predict the anisotropy tensor, and this is the anisotropy tensor, which is normalized by 2K, and the K can be calculated by half of normal Reynolds stresses. I want to predict this. I input BIJ tensors in my ML model for training, and predicted for low fidelity data. This is the LES, the 6 component for a square duct anisotropy tensors. You can see this is for high fidelity, and we want our result to be like this. And this is the result of CNN. The left part is RANS, the middle one is CNN, and the right is the LES. you can see the discrepancy between the rightmost one and the leftmost one. There is a huge discrepancy, and with CNN we decrease the discrepancy. The same scenario for B23 also. And the results for periodic fields. The left one is also the RANS, and the rightmost one is Elias, and the middle one is CNN. Again, you can see how this discrepancy decreased. Also for B12, again, the same situation. For converging diverging channel also, the left one is also again RANS, and the right one DNS. You can see how the result, how the model is increased, enhanced, RANS. Oh, sorry. And again, this one is for B12. So I have some conclusions. In any case, I increased the RANS model drastically, but it is the applicability is under question because neural network considered as a black box model, and as I said, neural networks probably can be better than any other ML frameworks, but we cannot extract equations. To my knowledge, only the field inversion and machine learning and gene expression programming are the two methods that they used. They extracted equations. Probably some new symbolic and different symbolic ML frameworks can be implemented to insert it into the CFD code, which is my own plan to do some symbolic, to implement some symbolic frameworks, ML frameworks. And this is the key references. Thank you for your attention. Sorry for my voice.
Thank you. So, yes, please, questions. Do you have in plan to verify algorithms by not simulations but by experimental data?
This is the aliens data. This is they consider it as high fidelity data. So experiments.
Yeah, it's high fidelity, but it's obtained from the models. Yeah.
Yes, I understand, but those need a lot of infrastructure, I think.
I can add the comments from the experiments. Often it is not possible to extract so much information like from the numerical simulations, and the most of methods need different complicated tensor functions to be inserted for training. So direct numerical simulation results are better than the experimental results. But we can, of course, compare results of direct numerical simulation with laboratory experiments. If they are identical, then we can trust the databases for direct numerical simulation or for large video simulation.
And maybe you know what is the area of discrepancy where the experimental data may differ from the model one, where the main discrepancy appear.
This is because of mathematical. We have, this is the Navier-Stokes equation. we cannot solve this directly because it is computationally expensive. So we will do some mathematical assumptions like time averaging, and it will become runs. So because of this time averaging, this discrepancy appears. This is my idea. I don't know.
You can see extra term, which is Reynolds stress. It is unknown term, and it is a source of discrepancies.
Mhm.
The last term of this equation. We cannot know it in advance.
Yeah, I just want to realize how it looked like if we where the discrepancy appear in real experiments, what our model doesn't cover.
There is
how it look like. Okay, it's stress tensor, we cannot model, and that's why we will obtain some effects in flow.
If we compare the results of the laboratory experiments and of simulations, there are discrepancies in the mean velocity distributions and in distributions of mean pressure. Okay, and also the Reynolds stress values may be different in the experiments and in the simulations. And the reason is because we don't know exact values of the Reynolds stress in advance. We should evaluate it somehow. Okay, this is one of the reasons of uncertainty for the model based on Reynolds average approach.
Okay.
Also, there are other levels of uncertainty connected with the averaging procedure itself. You see here, we move out all fluctuations actually. We consider effects of unsteady fluctuation behavior only by the Reynolds stress, which is not different, which is different from the direct numerical simulation, where unsteady behavior is taken into account via nonlinear convection term, which can be seen at the left-hand side of this equation.
Okay. And maybe other questions?
Maybe I can add some more notes. I can say about the ML model. One of the critiques that people say is that we cannot extract equations from neural networks. That is why I personally started to implement, if I can implement some symbolic approach to get some equations, then insert it into the solver and have a new CFD model, not ML.
Okay, it's also possible. Okay, so thanks again for presentation.
Thank you.
And we are going to next. So now we have listened to the turbulence models with the help of convolutional neural networks. And the next speech will be about the application of, again, convolutional neural networks, but like small advanced, like a mobile net with self-attention to the problem of cancer recognition. Just ask if the speaker present here, Alexander Savelev, are you here? Yes, so the talk is entitled as two-stage self-attention-based neural model for lung cancer recognition.
Здравствуйте, меня видно, слышно?
Да.
Да. Здравствуйте, меня зовут Савельев Александр. Я представляю работу a two-stage self-attention-based neural model for lung cancer recognition. Данную работу я выполнял вместе со своими коллегами Алексеем Самариным и Валентином Малykh. Ежегодно в мире от рака легких умирает около 2 миллионов человек. Это онкологическое заболевание является одним из самых смертоносных раков в мире. Одним из способов обнаружить данное заболевание является компьютерная томография или сокращенно КТ. В отличие, например, от рентген-исследования, КТ позволяет увидеть детальное изображение органов послойно, то есть представляется в виде серии изображений с различных срезов. КТ является одним из самых надежных и прогрессивных методов диагностики самых различных заболеваний, не только рака. На сегодняшний день очень распространены сервисы онлайн-медицинских консультаций, такие как Яндекс.Health, Amwell, BetterHelp. На этих сервисах пациенты могут получить консультации от врачей, и также не только от врачей, но и от алгоритмов машинного обучения. Например, часто пользователь данных сервисов может поделиться какой-то фотографией КТ-снимка, чтобы получить какое-то альтернативное независимое медицинское заключение по этому снимку. Таким образом, наше исследование посвящено проблеме распознавания наличия новообразований на монохромных снимках компьютерной томографии легких. То есть рассматриваемая проблема может быть формализована как бинарная классификация монохромных изображений, где один класс представлен в виде бинарного изображения, где есть новообразование и где нет его. На картинке представлен пример таких изображений. Слева с новообразованием картинка и справа без. Датасет для обучения, валидации и тестирования составляет чуть более 10 тысяч фотографий КТ. Этот датасет является комбинацией нескольких датасетов. Большая часть набора данных была взята из датасета московской радиологии. Также еще данные были взяты из Cancer Imaging архив. Так как новообразования распределены не по всему снимку КТ, а сосредоточены только в полостях легких, мы приняли решение использовать двухступенчатую архитектуру. На первом шаге мы детектим полости легких, а на втором этапе мы определяем наличие новообразований на каждых из полостей с помощью классификатора. Для того, чтобы детектировать области легких, мы использовали SSD, Single Shot Multiplex Detector. Он состоит из backbone сети, который используется для выделения признаков, а также сверточных слоев, которые выделяют области на изображении. Для того, чтобы уменьшить время инференса и количество занимаемых ресурсов, мы использовали в качестве backbone сети MobileNet. Данная архитектура была создана специально для мобильных устройств и показала высокие результаты на датасете ImageNet. Ее компактность, маленький размер также играет большим плюсом в использовании для онлайн-сервисов. На втором этапе мы решали задачу классификации. На вход модели поступали полученные на выходе данные, которые получились на выходе с предыдущего шага. В результате наших исследований у нас получилась модель, которая использует в качестве фичи экстракшена ResNet 50, а затем использует multi-head self-attention. В будущем мы назвали такую архитектуру multi-attention over ResNet 50. Также мы подобным образом называли другие архитектуры, которые используют разные бэкбон и разное количество голов. Также у нас в качестве бейзлайнов наша задача выступала несколько моделей. Одним из них является EfficientNet, данная архитектура является state of the art на датасете ImageNet. В отличие от традиционных подходов, которые позволяют масштабировать размеры сети, такие как ширина, глубина, и в данной архитектуре такие параметры подбирались с помощью AutoML, которые позволяли фиксировать данные параметры. Мы взяли предтренированную EfficientNet B4 на ImageNet и файн-тюнили для нашей задачи. Вторым бейзлайном является LNet. Это кодирующая часть UNet. Мы выбрали такую архитектуру, потому что UNet была изобретена для решения задачи сегментации на медицинских данных, и для данной сети не нужно большое количество данных, чтобы ее обучить. Данную архитектуру мы обучали с нуля на наших данных. Третьим бейзлайном является ResNet-50. Эта модель особенностью данной модели является использование skip-коннекшенов, которые позволили также получить высокие результаты на датасетах ImageNet и в свое время быть state of the art на данном датасете. Для нашей задачи мы использовали претренированную ResNet-50 на ImageNet и также дофайн-тюнивали наши задачи. Self-attention – это модель, которая реализует концепцию внимания на сверточных сетях. Данную модель мы взяли из статьи про генерацию изображений и тренировали для нашей задачи. Также мы сделали multi-attention для данной сети с несколькими головами. В результате у нас получились на данной таблице у нас представлены результаты наших бейзлайнов, так и наших решений. Стоит отметить, что использование ResNet-50 в качестве фичи экстракшена и multi-attention показало самые высокие результаты. Также стоит отметить, что использование LNet в качестве фичи экстракшена и добавление к ней self-attention увеличивало скор по сравнению с тем, если использовать просто LNet. И даже перебило EfficientNet, если одиночную сеть. Так у нас задача классификации. Мы использовали стандартные метрики для стандартные метрики F1, Precision и Recall. В качестве результатов мы представляем датасет, который мы собрали для нашей задачи, и новый подход, с помощью которого мы решаем нашу задачу. У меня все. Спасибо за внимание.
Спасибо. Please, questions?
Hi, may I have a question?
Yes, yes.
Alexander, have you used any kind of visualization of your results? Do you have regions where you see these problems in lung or not?
Сейчас. Можете повторить, пожалуйста, вопрос?
Вы как-то понимаете те области, в которых у вас проблемы в легких, или вы только классифицируете? То есть вы делали какой-нибудь instance segmentation?
Так, ну, у нас был датасет, по которому мы просто делали. Вот. То есть не очень, если честно, понимаю вопросы.
Ну, на легких вот это вот место, где новообразование, вы как-то понимаете, где на картинке это место? Или ваш датасет просто не позволял, у вас датасет был классификационный, и там не было сегментации?
Нет, ну, мы также смотрели глазами наши данные и, то есть, сами научились понимать, где. Вот, например, вот на данной картинке находится вот здесь это новообразование.
Нет, я понимаю, Александр, а сеть нейронная научилась понимать или нет? Или сеть нейронная только классификацией занималась?
Вы имеете в виду детекцию? То есть,
да, object detection, localization, да,
мы
и так
решали
далее.
только классификацию пока.
Да, в этом и был мой вопрос, спасибо.
Да.
Меня слышно?
Да.
Алло.
Да.
Наконец.
Так, ну, починили просто. Вопрос такой, то есть у вас задача классификации сводилась исключительно к отличению нормального легкого от любых новообразований, которые вы наблюдаете, или вы смотрели все-таки другие патологические процессы, воспаление, различные, собственно говоря, морфологические изменения, которые к патологии относятся, но не являются новообразованиями?
Спасибо за вопрос. Мы использовали для датасетов, в которых именно были новообразования, как для рака. Вот.
Ну, онкологические заболевания, если корректно говорить. Понятно. То есть, если мы бросим эту сеть в медицину, то она, ну, скажем так, даст достаточно большое количество ложноположительных результатов по всем смешанным случаям, где есть другие виды патологии. Амилоидоз, гиалиноз и так далее.
Ну, если прям вот эту сетку, то да, но это же будет разные тематики совсем. То есть нужно будет эту сетку, да.
Тематика, она простая при классификации, чтобы у вас здоровое легкое от различных патологических процессов отличать. Вы просто сейчас решали задачу классической диагностики, а необходимо решать, помимо всего прочего, задачу дифференциальной диагностики. Обсудите с руководителем.
Да, хорошо.
Спасибо. Можно вопрос? May I ask question? So should we speak in English? Прошу по-русски, раз уже доклад был на русском.
Можно по-русски, да.
Да, рад всех видеть и слышать здесь. Вопрос по сравнению с другими программами. То есть сейчас эта тема очень популярная, анализ биомедицинских изображений, классификация, в том числе на легких, в том числе в связи с ковидом, анализ данных, предсказания и уточнение моделей. Делали ли вы сравнение с ковид, какие-то данные?
Мы решали исключительно нашу задачу и смотрели, как, то есть Efficient.net, LNet, ResNet, мы смотрели, как другие решают, и отсюда и бейзлайны.
Хорошо, спасибо. Не будем тогда задерживать доклад. Thank you for presentation. Please continue.
One more question. Have you only one type of cancer considered? Только один тип рака рассматривали или разные? Они же разные раки.
Мы брали именно датасет и по нему, то есть мы не совсем врачи. Вот, и мы только, получается, один, как я понимаю.
И есть ли понимание о быстродействии разных вот сетей Efficient.net, ResNet, они там по количеству параметров обучаемых различаются?
Мы брали ResNet 50 и Efficient.net 4, мы брали именно по примерно равному количеству параметров. Вот. Отсюда и брали ResNet и Efficient.net 4.
Okay, if any other questions? So if, no questions, then thanks to the reporter again. Thank you.
Спасибо за внимание.
Спасибо. Okay, so now the supposed reporter next, Ashi Arvind Gala, that's with evolutionary algorithms during COVID-19. He is not appear, and he wrote that he cannot present due to health issues. And so I ask the last presentation of today, Mukul Vishwas, to present now. Mukul, are you here? Can you deliver presentation?
Yes, I am here.
Okay. So please start.
So are you able to see my screen and hear my voice?
Yes, yes.
Okay. So hello everyone, my name is Mukul Vishwas. I'm a student of Novosibirsk State University. And today I want to present face mask detection model using MMdetection framework. And my scientific advisor is Mr. Alexey. So let's start without delaying any time. So this model is a sub part of my master thesis. My master thesis is divided into three parts. First, I'm going to do object detection, which is the main part of this presentation, and I'll explain object detection in this presentation. But sorry, in this object detection, I implement an object detection model, and I have to fine tune it, and we are currently working to implement this on live model. We are fine tuning it, and for the second phase of this project, we are going to extract features from the object detection model and represent it in a space representation, and we will use those feature space representation to track the object in the model. And in simple words, if I say, we will track the single object in a video, and the boundary box and the track should move with the object. So it just not detect the object, it should give it a specific identity, and it will move with the object, and it will track while the object is in the frame. And for the final part, we will quantize our model. And what I mean by quantization is we will reduce the size of our model so we can improve the performance. And it should store in small size device, and it should be very easy to download, and it will use less memory, and it will accelerate the compatibility of our model. So these are the content of my presentation, and I'll explain everything while we move further with the slides. So let's go to the first slide, which is the problem statement. As we can see, we are having a pandemic of COVID-19, and it's cost more than 1.2 million lives. But we can avoid this by just following some basic hygiene rules. Like washing the hands and wearing the face mask. So in this presentation, we implement a model which will discriminate between the peoples, those who are wearing the mask and those who are not wearing the mask, and a third class of the people, those who are wearing the mask incorrectly. So as I said, we used MMdetection models. So what is MMdetection model is? It's an open source object detection toolbox. It is based on PyTorch. It is very faster in computation because it's run only on GPU. That's why. And it's used different detection framework, and all those frameworks are shown in the next slide. And it's use different dataset which are in Pascal, Coco format, and XML. So these are the different framework it can support. As you can see, it support more than 15 framework. And if we compare it to the different object detection framework which are right now out, like Detectron, SimpleDet, it's support twice as detection framework as compared to them. So what is this model? So this model is, you can see, is divided into 4 parts. It's the big backbone. I use ResNet 50 for the backbone, and this is mainly used for feature extraction. And these features then feed forwarded to its second part, which is feature pyramid network, which extract features. And this feature pyramid network is highly computational cost. It increase the training time, but it reduces the test and validation time. And we have dense head and ROI head. So I will tell a little bit about ROI head. ROI head, the main function of ROI head is to detect the object and draw the boundary box and mask on it. And dense head, once we get the region of interest where we have to detect the object, it will extract feature from it. So this is the complete model of the MMdetection. So if we see here in this slide, so this is the flow of the data in the MMdetection with and without a feature pyramid network. If you can see, without, if we compare the architecture with and without FPN, here you can see this is the main magic what happened in feature pyramid network. So as we decrease the size of images, its semantic value increases. So visually we can see it's getting a little blurry, but it's very good to extract the features. So that's why I use feature pyramid network in this MMdetection. It creates the pyramid of features. So the bottom layers are not selected for object detection. They are high resolution, but semantic value is not high enough to justify its use, as the speed slow down significantly. It slow down its size significantly. So in case of a data set which is very big, so if we are input a lot of images with different resolutions, so our model have to go through each and every images and extract the feature from it. It's a very time consuming process. So what feature pyramid network do is it create feature pyramids from a single image, and it works on that single image. So extracting the feature takes some time, so it increase the training time, but it increase the accuracy of our model as well. So if we see the comparison of the performance with and without feature pyramid network, our training time is slow without FPN, but with FPN it increased. And dataset requirement is big for without FPN and small for with FPN. And test and validation time is high for network without FPN, and it test and validation time decreased if we are using feature pyramid network. Accuracy is also increased, and average recall is also increased. The detection of total positive samples or the images is also increased, and inference time, the time taken to predict an image is also decreased. So overall, if we use feature pyramid network, it will increase the accuracy and performance of our model. In the next slide, I want to show how I annotate or create my data. So to annotate, I use ImageMe tool, and this is the output of that tool, how I create the annotated file. So if we have to annotate each and every images and show how many classes we want. So this image was annotated with mask and without mask faces only. After that, it will create a JSON file for each and every images, and we have to convert those files to Coco format to feed into our network. So as I explained all this thing in the model architecture, so in this slide I'm going to show you the training loss for my model. So here you can see I used 200 epochs to train my model, and in initial 25 epochs you can see the loss went from 10 to 1.73 and it decreased gradually. So I hope if we train our model for more than 200 epochs, like 1000 epochs, it will perform better. I use stochastic gradient descent for optimizer and learning rate of 2. Instead of showing traditional approach how this model looks in graphical format, I use dictionary format to show how training and testing process took place. So as you can see, from loading the data to then resizing took place, then random flip, it's just the augmentation technique. And after that, we collect the output in the form of images, boundary box, and the labels. In the process of testing, we just take the image, this process are same, but we take images with the boundary boxes and mask. So just this is the difference between the output of training and testing phase. And in the next slide, this is the output of my model. As you can see, it's correctly able to predict the incorrect way of wearing the mask, incorrect way, and no mask, and mask face. And threshold for my model is 90%. So if the model is confident more than 90%, it can show the boundary boxes around the face with the class, like incorrect, correct, or mask face, or in no mask face. So the object detection framework work on IOU area under IOU. So it's a very new approach for object detection. So as you can see, if I want to, before showing my result, I want to just explain this, how this is calculated. Area over union. So if this is our prediction of our model, and we annotate it like this way. So red boundary box shows the ground truth and green show our prediction. So in below image, you can see this is the union of that area of ground truth and prediction, and this is the intersection. And if our model predict and the intersection is greater, or intersection is intersection area is equal to or is very similar to the union area, IOU reaches towards 1. So it means our prediction is better. So the bigger the IOU, the good our prediction is. That's how the object detection accuracy calculated. So in the next slide, this is my result. As you can see, mean average precision for my old model is 0.215. It's I can say not very high, but after tuning the parameters, it reaches to 0.43. And this is compared, this is very good. We can see almost twice improvement in our model. And if we can see, IOU is denoted or showed from 0.50 to 0.95. What does it mean? It means the mean average precision value from 0.5 to 0.95. This is the confidence, and this confidence is calculated with 0.05 step size. So this is the average from 0.50 confidence to 0.95. And you can see there is slight improvement, and we are trying to improve this furthermore. And we are very confident that we can improve it to 0.50. That's a pretty good accuracy for any object detection model right now. So the future task for my model, which are training the model with more data. to increase the accuracy, and we are fine-tuning our model to implement this on live video streams. And yeah, the final task we have to do is the quantization of our model, so we can use it on very small device like Jetson. So that's all from my side. So thank you for your time, and I want to wish you happy Diwali.
Great, thanks.
Thank you. It's very interesting presentation. Don't very actual for our time. So my some question. So have you trained only on white mask or using different colors? So because sometimes shapes of the face masks are very different now, and people use something else.
So yeah, we tried different type of mask, and for our model, the different color and different shape of mask doesn't matter. We train our model with different mask and different face size and different color. So it doesn't matter, we try different shape or color. It will able to detect different type of mask as well.
Yeah, it's a good notice to mention it in the paper. That you tried this color, at which amount it appears in your training set, in your test set, to describe it. Like, it's very important.
Yeah, actually we used 158 different images with more than 3,000 annotations. So it's a very wide data set, and we have different scales as well. So if the face mask is very small or very blurry, so it's able to detect it, but we have to increase the threshold. We have to decrease the threshold. So it's a compromise between the threshold and the quality of the images.
A minimal comment for Yuri. The main task is a screening identification of masks at this stage.
Yes. Right now we are working on only detection, and further we will implement feature extraction and quantization. So this presentation is only for detection. And I hope I am able to present the next part in the end of the December.
And also, I recommend to disclose the data set, either to publish, either to describe in the paper the how you constructed the data set. Maybe it's not less actual than the paper itself, than the algorithms results itself. Yeah.
Okay, I'll do that.
Other questions, maybe comments? Okay, if no questions, thank you, Mukul, for presentation.
Thank you everyone.
So let me show our plan for today. That's we already covered the first section of our conference, and we moved one report from the end of today, that's face mask detection, to this section. And now we have time for discussion, and actually also for break, lunch. That was so the interrupt will be till 1 hour and 20 minutes. And now I suggest some topic for discuss. Like we already listened to actually convolutional neural networks applied to 3 different domains. First was turbulence flow modeling, second was cancer recognition, and the third was what correctly how to name this domain. It's surveillance or face recognition, right? Or what is kind of domain it's applied. So different domains. And to make the discussion sharp, like, I want to ask if the things will go that way, possibly after 5 years, the convolutional neural networks will do all the current work of scientists. What will be the future shape of scientists? Like, will it appear as main tool for scientists?
You are too optimistic.
But you are developing these tools, as I see. You should be optimistic also.
I presume.
What do you think about maybe some framework needed for scientists, or we just can use this wide-known PyTorch or TensorFlow, or we need some specific one for especially for scientists?
No, I presume, Eugene. There is no need for specific algorithms, as common sense must be solved with the common algorithms. Any specific algorithms do not work in the any environments that have some changes from the initial environment.
Yeah, but I suggest possibly a tool for creating data sets, like some some requirements for scientific data sets should be met, like the variability of data set, the correspondence to particular task. We need to be sure about the data set we are taking for our investigation is good data set to apply some specific algorithm.
That depends on the task, as you understand. Some problems of classification are rather large, and in case of medicine, it is a very, very complicated task to formalize a very good data sets, as what I can see in the current landscape in the machine learning. The current data sets are very awful and are made usually by non-specialists in machine learning or in the field, or in the specific field, like in the medical field. And this is a problem. The specialists must have knowledge on both spheres, on both fields of machine learning and the specific field to have a good data set.
May I add some words?
Yes.
When preparing data sets, we encountered that it's a very time-consuming task and labor-consuming, and you need to have 2 or 3 several kinds of persons. First one, those who understand how to annotate data, other understand which instruments you can use to annotate data, and some people coordinating it. And now I should say it's a very complicated task to prepare a good data set. What I see the mainstream is just to provide researchers and maybe other professions with a good tool to annotate data sets by themselves. Probably it would be nice to have tools to annotate several hundreds or maybe thousands of instances, and just to train some publicly available network and to see the result. I think that it would advance deep learning very nice.
Well, I think that the problem is not only the data set. Actually, as we saw in the keynote by Alexander Shapeev today, he actually mentioned a very important topic, which is a combination of connectionist approaches together with other approaches, like symbolic-based approaches. This is a question of how an expert can combine data together with mathematical models to benefit from the both worlds, actually. Because, well, if you forget about mathematical models, if you forget about knowledge formulated in the form of models of any kind, then you lose a big part of the world. You're doing only data, and this is like only one side of the problem, only one view at any problem that you get, because these are complementary worlds actually. Learning from data is like making decisions based on intuition. You gather some experience during your life. You gather some data, and then you make conclusions, you make predictions based on what you have observed. This is very important. But another way of making conclusions is to use knowledge, and knowledge can be gathered as well. It can be summarized, and this is another world. And actually, well, connectionist approaches, well, for instance, neural networks are often opposed to knowledge-based approaches, but actually this is the wrong way, because we should benefit from the both worlds. In this sense, I think that if we think about the tools of tomorrow that expert in any kind of field is going to use, I think these kinds of tools should try to incorporate the both worlds, so mathematical models and data.
Yeah, Denis, I want to confirm, accept, and appreciate it with this approach. Yeah, actually, from the first report, we see that all the data was generated by some knowledge, yeah, by some models, incorporated knowledge, some computational fluid dynamics, direct numerical simulation, and the runs models are models, and some it's like data generated by knowledge. That's why I asked maybe some experimental data, the response from the nature, yeah, what we want actually to train from. And this possibly tools of two kinds. One tool is to label data sets, to label manually, right, to train artificial intelligence with real data obtained from the nature, and second tool to be able to generate from any kind of knowledge, whether it's mathematical, logical form, different forms.
Right. This is one more way to go, because if you really do not have enough data, you may produce it either from your mathematical model, which is nice, or from, well, a pre-trained model, machine learning model, right? So there are both ways again. So again, you can do both, either use knowledge or use a machine learning model, which has been trained, well, on some other data, for instance, or it can incorporate knowledge.
Yes. Yes. So I also see one interesting question. That's maybe not question, just remark, that from the from the first invited lecture from Sergey Igorevich Kabanikhin, he said like some methods of artificial intelligence can be applied for solving ill-posed and inverse tasks. Actually, and vice versa, some ill-posed solutions can be applied for artificial intelligence. So we have a back and forth like an approach to maybe like one of some turbulence models can be applied in neural network training. So we need to keep in mind that like both directions are possible. Like in quantum mechanics, some machine learning model can be applied for quantum mechanics equation resolution, and some quantum mechanics can be applied for machine learning, like quantum machine learning. It's two directions every time it's possible.
Yeah. Evgeny, may I add one more word?
Yes.
It's interesting question about the balance between knowledge produced by another model or knowledge ab initio and knowledge or annotations produced by a person. And I should say that when we arrive to the problems which are very complex, and many real-world problems are complex, I should say that turbulence problem is not so complex as another real-world problems. For example, driverless cars, self-drive cars are much more complex than turbulence problems. And when we arrive to such a problems, we need person. No one understands how a person arrives to the solution. And however, person arrives to the solution, and we know that a good person arrives to the good solution. And what we need just to copy this behavior. And we cannot understand how we copy this behavior. And this is the case of deep learning models. They have so many parameters that it's very difficult to understand how do they arrive to the solution. However, we can effectively train them, and they copy our behavior. That's very interesting balance between what we understand and what we don't understand. In fact, we even often don't understand each other. Despite we speak the same language and operate with the same ideas. However, we don't understand each other, and we teach each other. We understand on examples what we want from another person. And I should say that this is the case with deep learning models. We show them what we want from them, and they just try to teach from that. And again, I want to point out that making these models more available for broad public would much increase the level of penetration of this technology in our life and the technological advance, technological rate. Thanks.
Yes.
Alexey suggested a very important thing, that we are a part of a larger structure, the integrated ensemble of neural network, and the researcher as the larger neural network with the back propagation. And you understand this is a very, very, very important part. The researcher must be in this ensemble.
Artificial extension of brain, yes.
Yeah.
Yeah, actually, Alexey pointed out that the question about we possibly falsely we can come to in a false imagination if we approximate our decisions by logical way. Yeah, so some explanations can be given about our logics, about our knowledge, but what deep learning models discover that many unlogical way of reasoning can be done, and it works in real applications. So Actually, the combination of these two should give us new perspective of applications in science specifically. And yesterday I saw a presentation from Ivan Bondarenko about like people 50 years ago thought about artificial intelligence in as logical, something that model logical reasoning of people. And that's why they try to test people to artificial intelligence contest in tasks logically way, like formulated, like chess, how to win chess party. And then, like in 90s, we discovered that computer completely can overbeat people by chess, but no computer now can solve like task of football playing. It's rather less intellectual work than chess. Anyway, no computer can do this. That's possibly it's more intellectual way. Yes, Nikolai Vyacheslamovich.
Nice to see all of you. Hope you hear me. Do you hear me? Great.
Yes, yes.
I would like just to draw attention of the community to, well, from my point of view, very important issue. Formal verification of artificial intelligence systems that is needed indeed. In particular, I would like to be very short. Just a week ago, we had a workshop, program semantics, specification, and verification. And one of invited talks was given by Ekaterina Komendanskaya from Harvard University. She is head of laboratory of formal verification of AI systems. Later, I can share a link to her indeed very interesting, let me say, fascinating. I would not like to say great, fascinating and interesting talk. This issue is indeed, in my vision, very critical. First, because I am from verification community, but would like to understand better from this verification point of view, artificial intelligence. It is my first comment. May I give another comment? May I?
Yes, yes.
Well, the first comment was just to draw attention of people. Next comment is about, well, what did you just say a few minutes ago about artificial intelligence and chess, artificial intelligence in football, so Robocop or something like this. This time, I just would like to say a few words about so-called International Mathematical Olympiad Grand Challenge. It is related, it is much more similar to chess rather than to football or soccer. If you would like soccer, if you have American participants, well, but the problem is to implement this challenge was formulated a year ago by a group of people, including maybe I'm not sure, but maybe initiative came from some people from Microsoft Research to build artificial intelligence that will be able continuously win golden medal in International Mathematical Olympiad. The challenge here is threefold. First, to implement artificial intelligence that understand quite formal, but nevertheless natural language formulations of problems for International Mathematical Olympiad. Then, to force theorem prover to solve formalized problems. And the most complicated, most challenging part, to represent solution in human readable, jury readable format. That's all. It is, I believe that it is much more similar to chess, but chess is much easier to represent. Thank you for your attention. So two messages. First, about formal verification of artificial intelligence systems, in particular hybrid systems with artificial intelligence, autonomous cars. And next about International Mathematical Olympiad Challenge. Thank you for attention.
Thank you. Yeah, I just remembered that in the end of last year, Facebook presented a paper. They used artificial intelligence, especially neural networks, for symbolic computations. So they trained neural networks in order to differentiate and integrate equations. And like you know that we can easily generate a lot of correct differentiation integration operations and easily train neural network from learn to symbolic corresponding from this form after differentiation in this form. And they train and show that the neural network approach they presented is more powerful and more correct sometimes than real like Wolfram alpha simulation or real symbolic computations. And of course, it's not like 100% accuracy, but it sometimes provide more fast solution. And sometimes solution appears for the equation which are not symbolically resolved. It's very interesting approach also. So yeah, I confirm that it's possibly people will develop in AI solving mathematical problems, mathematical equations, and this grand challenge possibly one of these attempts. So have maybe someone also wants to say, add to our discussion? If
one comment, another. As you can see, to provide us with information, medical tasks, very important case in medicine. There is a special pipeline to identify any final classification is a screening level. When you must identify that are like similar to the problem, but are not certain solutions of the problem. And this part can be solved by any algorithms as a level of classifications. The differential diagnosis classification is a much more complicated task. And this level cannot be solved without any pipeline like Alexey Grigorievich suggested with the extended neural networks system with the back propagation from the real intelligence. And this is a very, very, very important case which can be applied for any classification tasks. Medics have a very good knowledge, but they don't understand the idea of this knowledge. And it can be understood only by a few specialists. This is the short comment on these problems of classification.
Okay. Okay, so thanks for participation in this fruitful discussion. So we have now 1 hour break for a lunch, and then we continue with the presentation from Ivan Bondarenko and his team using few-shot learning techniques for named entity recognition and relation extraction. That is application to linguistics. Okay, so we're having break.
Чому ми дивимося на зірки, птахів і природу навколо нас? Це краще зрозуміти їх або нас. Чи це тому, що ми шукаємо абсолютну правду? Але абсолютна правда, яку ми маємо зараз, це дані. Дані є справжнім і використовуються для передбачення майбутнього. Дані можуть бути чимось, що нам потрібно, як вода, щоб вижити. Але це може бути просто тенденція, яка популярна до тих пір, поки триває смак. Або, може бути, це щось неминуче, або проходить повз нас. Тут студенти і викладачі в області наук аналізу даних і магістерських програм працюють на краще майбутнє даних. І ми прагнемо поєднати дані, абсолют і природу в одному місці, яке ми називаємо домом.
Good evening.
Good evening.
So our presenter is here, I see. Откуда эти звуки?
Даже не знаю. Евгений, думал, что от тебя.
Это от меня, да. So, I'm glad to present our next speaker, Ivan Bondarenko, who will present the paper using few-shot learning technique for named entity recognition and relation extraction. So you have 30 minutes.
Okay, thank you. My speech will be short, and I am glad to present the results of our research. Now I share my screen. 1 minute. Do you see my screen? Do you see slides?
Yes, we can see.
Okay, okay. All right, I can start. Area of our research is few-shot learning for natural language understanding. I took part in this research with my colleagues Sergey Berezin, Alexey Pauls, Tatiana Batura, Yulia Robsova, and Bair Tuchinov. And we are from Stream Data Analysis Machine Learning Lab of Novosibirsk State University. And what problems do we solve? Named entity recognition is a task for semantic analysis of a natural language in Russian or in English or in another natural language. For example, we have some text, United Nations official chaos heads for Baghdad. And in this text, we can select morphology information, part of speech, etc. We can find syntactical tags, and we can build dependency tree. And the third layer of understanding is semantic layer. And named entities is a typical kind of semantic layer in natural language understanding. But we can unite entities in special relations. For example, we have entity person, chaos, and we have entity United Nations official. And what relation between these two entities? Affiliation, a chaos affiliation is United Nations official. And what relation between a chaos and Baghdad? Traveling. Chaos heads for Baghdad. These two kinds of semantics, named entities and relations, are natural language understanding task. Natural language understanding equal to named entity recognition plus relation extraction. And this is a very important task for many applications. For example, we can parse news stream, and we want to find special events in the news, or we can analyze scientific papers or technological documentation, and we can find entities such as K terms, events, etc., and their sentiment or relations between another entities. And a classical approach to solve this task is supervised learning. We have many pre-trained models for text processing, from simple models such as word-to-vec or fast text to more complex and more powerful models based on contextualized representation of language, Elmo, BERT, etc. And these models are pre-trained model. Training set and task for pre-training is language modeling in common lexics, in common domain. So if we want to build named entity recognizer or relation extractor in a special domain, then we need to fine-tune our model on annotated texts from this domain. And this is a very big problem, because annotation, manual annotation of text is very hard thing, particularly in special domains such as chemistry, oil and gas, engineering documents, etc. So we can use one kind of supervised learning, few-shot learning. Few-shot learning is based on using little labeled datasets, for example, hundreds or tens of labeled samples for each class. And there are two popular ways for solving few-shot learning problem. One of these ways is metric learning. You know about metric learning, for example, if you know about Siamese neural networks. Siamese neural networks is a well-known technique for training, for machine learning training, and it was applied for computer vision. For example, one of first papers devoted to metric learning is Siamese neural networks for one-shot image recognition. And for natural language understanding, for computational linguistics, there are some research in this area, in metric learning area. For example, one of these papers is few-shot classification named entity recognition task. This research is based on one variant of metric learning. Yet another interesting area, research area in few-shot learning, this adversarial learning. We can use special neural networks based on generative adversarial networks or variational encoders, and we can train to find common things between two representations of our objects, between objects and classes of these objects. After that, we can generate one representation, object representation, by class representation, and class representation. We can generate class representation, but object one. There are many papers devoted to this area. For example, generalized zero and few-shot learning via aligned variational encoders. This is well-known paper in 2019. Yet another paper is based on hybrid model, variational encoder with generative adversarial network. And for name and entity recognition, we know also some papers in this scientific area. For example, MetaNer, name and entity recognition with meta-learning. This paper was published in this year, and it is very interesting. But we want to propose a third approach, which is very simple. Our idea is based on adding of a priori information about sentence structure in the deep learning model. Base of our algorithm is deep learning model, such as BERT or ELMA, but we add a priori information about a morphological and syntactical structure of sentence. As we know, adding of a priori information is maybe a form of regularization of our model. And for one of first examples of this approach in deep learning in neural networks is convolutional neural networks. We use information about image structure and about neural vision system in human for distillation of our neural network. And we use not fully connected neural network. Convolutional neural network is based on receptive fields, shared weights, etc. This is a typical example of using of a priori information using. But we propose another approach. Each language has special morphology and syntaxes. Morphology is syntaxes, and syntaxes are universal objects for any genre, for any style of text, for any special domain in this language. But named entities are very individual objects. They are different for chemistry, for engineering, for physics, etc. And so we can base on common morphology and syntaxes. After that, we can fine-tune our deep learning model with additional information about morphology and syntaxes in concrete sentence. If we want to build named entity recognizer, for example, if you want to build a named entity recognizer, then we need to retrain this NER into annotated text. But if we apply morphology parser in special domain, we don't need to retrain this morphology parser. This is a key concept, and we were inspired this idea, and we propose special framework, few-shot natural language understanding. This is open source framework, and it has some features such as modular architecture. There are some possibilities of using applying for users. We propose pre-trained processing in our few-shot in our framework, or user can retrain from scratch, etc. And what architecture of our few-shot NLU? We can we can prepare labeled text in BRAT format. BRAT is famous utility for text annotations, for natural text annotations. And we have two main components, named entity recognizer and relation extractor. Then entity recognizer based on deep learning models as feature extractors, and we add special feature extractors, and we use special feature extractors together with deep learning, with distributional semantics. We use morphology and syntaxes and spelling. Also, we can add dictionary, which is generated from thesaurus. And after that, we add classifier component in named recognizer. Classifier component can be based on conditional random fields or recurrent neural networks with CRF. And the relation extractor is based on deep learning model as feature extractor 2, but classifier is a special neural head after deep learning base. Okay, what data pipe in our framework? For example, we have some sentence. Novosibirsk State University is located in the world famous scientific center, Akademgorodok. Our named entity recognizer tokenize this text, and for each token, and it find corresponding entity label for each token. For example, location entity starts from character 80 and it is finished in character 93. Location, Akademgorodok. Organization is Novosibirsk State University. Starts from 0 character. This is. After that, relation extractor takes output of named entity recognizer, and it recognizes all relations between all entities in this text. In this example, we see only 2 entities, and relation extractor classify relation between these entities, part of. Okay, what approach we use in this named recognizer and relation extractor? As I tell, we use deep learning based on transformer architecture. Transformer architecture contains of multi-head attention, positional embeddings, and byte pair encoding for special quasi-morphem tokenizing. And outputs of pre-trained transformer model we use as embeddings, as special semantic embeddings of our subtokens. After that, we apply morphological parser and syntactical parser to this sentence, and we combine outputs, distributional semantics as outputs of BERT, and part of speech text and dependency tracks from dependency tree from, for example, UDPipe parser. After that, we get united representation of tokens in text, and we apply simple machine learning models such as conditional random fields, and we get few shot solution with a good generation ability. But what few shot properties of this solution we need to check? We use 2 datasets for experimental checking. for named entity recognition, we use factorial dataset. This dataset was devoted to recognition of 3 types of entities: organizations, locations, and persons on Russian news. We have only 122 label texts for training. This is a small number of texts, and 133 label texts for testing. And but this number is not few. This is not large, but it is not few. So we do a series of experiments. We randomly selected small parts from this training set, 16 labeled text, 32 labeled text, and full training set. And we train our few-shot name entity recognizer on these small parts of training set and estimate generalization ability on test set. As you see, F1 score with macro averaging of entity recognition is not very beautiful if we use a very small training set, but this is more than 0.6. So if we increase size of labeled data set from 16 to 32, then quality of NER increases too, radically increases. And if we train our models on full data set, then we get state of the art in this task. For comparison, you can see this table. These 2 last lines describe our results on full train set. Few-shot NER based on ELMO as deep learning base, and few-shot NER with BERT as deep learning based. And in other lines, you can see results of other researchers on this data set. And as you see, few-shot and NER with BERT and additional information about syntactical structure and morphological data about sentence is state of the art for this data set. But what about relation extraction? Our solution is not state of the art for relation extraction, but few-shot properties are saved. As you see, results of relation extractor on small parts, small subsets of full training set are increases, but if we get only 50 numbers, 50 texts, labeled texts of each class, then our results become stable. Data set for these experiments is based on Rurebus competition. There are more than 200 labeled documents in source data for these documents is data set from Russian Ministry of Economy. All regional reports to center were labeled by researchers, by organizers of this competition. and there are 4 types of entities and 11 types of relations between these entities: goals, task, temporal relations, etc. And our task is recognition of 11 types of relations. As you see, results of our relation extractor are few short. Okay. And what conclusions about this thing? I can tell that linguistic features in combination with distributional semantics from deep learning models facilitate the convergence of learning and increase of generalization ability of our NER. So our results in relation extraction domain are comparable to other researchers, but our results in the name entity recognition domain are state of the art. Future points of our research are end-to-end natural understanding. Now we use component by component architecture. But as you know, multitask learning is efficient technically for more efficient generalization. And we want to use end-to-end natural understanding with multitask learning, named entities and relations together with single deep neural network. And the second area of our future research will be in zero-shot natural understanding. Now we research a few-shot problem, but we want to research a zero-shot problem. This research will be based on combination of deep learning and special knowledge models based on thesaurus such as WordNet, ProverNet, etc. So this is finish of my speech. Thank you for attention. I'm glad to ask for your questions. Thank you.
Thank you, Ivan, for presentation. Denis, please.
Yes, thank you. I have 2 short questions. I am not very much familiar with relation extraction techniques. Therefore, my question are the following. The first one is, you mentioned binary relations. Do these techniques easily extend to relations of any arity, like 3, 4, and so on? This is the first question. And the second question, what if I want to reason about relationships over relationships? Like I want to reason about relation which is transitive, for example, like Alice is a boss of Bob and Bob is a boss of Charlie. Therefore, Alice is a boss of Charlie, right? So this is transitivity. So if you want to model this, how would you incorporate this into your model, or would you like to model this by external means, not by a network, some other means? So in this case, what would you do? This is the second question.
Okay, thank you for your questions. We solve relation extraction problem as multitask classification. We have many pairs, all possible pairs of entities in text. Entities were recognized by our named entity recognizer, and we generate all possible pairs of entities. After that, we use contextual embeddings for these entities from BERT or from Elmo, and we classify, we build united feature vector of 4 entity pair, and we classify each entity pair. If we have many kinds of relations, then this task is multi-class classification problem. And about transitivity in relations. Now we work with directed relations. From first entity to second entity in pair. For example, this thing has sense because my opinion is all relations have direction from one entity to another. There are no relations without direction. Such relations can be topic conditional relations such as goals or tasks in rebus competition. Hyponym relations are directed to, etc. And we, in our research, we work with directed relations.
So, okay, does this mean that you basically address binary relationships if you use directed relationships of this kind? Or you can still apply this direction-oriented approach to relations of arbitrary.
Excuse me, can you repeat your question about binary relations?
I got your answer to my first question, so that it is possible to manage relationships of any arity, but then you say you have directed relations, right? Directed ones.
Yes.
And then my question is, how do you use this when you have like ternary relations, for example, not binary? I can easily imagine binary relations as oriented ones, right? But
binary relation is variant of binary relation is a binary classification problem in this way. We solve multi-class classification problem for relation extraction because in our experimental tasks there are many kinds of relation, but in special cases, in simpler cases, we have only binary relation. There is relation between two entities, or there are no any relations between these entities. For example, hyponym-hyperonym relation is binary, and we can apply our approach to relation extraction for classifying of binary relations too.
Okay, yes, I see. Then I modify my last question a bit. Are there any data sets in natural language tasks for relationship extraction where you have not only binary but also ternary relationships? Are there any data sets of this kind?
Data sets devoted to binary relations?
Ternary.
No, which may contain binary relations to extract, but they also contain relationships of bigger arity to extract.
Тернарные, четвернарные.
Oh, okay, I understand. In our research, we don't see such data sets, and our goal was to build binary relation extraction. But in nature, there are problems with not binary relations, yes. But in many applications, we need binary relations only. For engineering documents processing or for oil and gas processing. And thank you for your comment. In our future research, we add this topic, not binary relations, in our research interests.
Yes, I completely agree that binary relations are, well, like universal artifact in many applications. This is completely true. I was just curious whether there exist data sets for training for relationship extraction, which are focused not only on binary relations, but also on ternary or some other kind. If not, then this would be a possible way to, well, just to develop your own data set, you know.
In simple case, I think that in a simple case, we can reduce ternary, for example, ternary problem to several binary problems.
Yes, absolutely. Absolutely.
Thank you.
Okay, so thanks for these questions. We thank again the reporter, Ivan, thank you. We are ready now to start the next presentation. Mukunda Das, are you here?
Yeah, can you hear me?
Yes. So this is a paper entitled "The Performance Monitoring on Industrial Rotary Equipment Using AI and ML Technique," and presented from India, Bangalore.
Let me just share my screen.
Yes, please.
Yeah. So the topic of my paper is performance monitoring of industrial rotary equipment using AI ML techniques. And this was actually done as a part of my final year project. I'm currently a final year undergraduate student in Bangalore, India. So first, to give you a little bit of a context about the usage of AI and ML in the industrial context. One second. Yeah. So this performance monitoring of industrial equipment plays a very important role, not only in maintaining quality in many of these industrial manufacturing plants, such as paint manufacturing, glass manufacturing, etc., but also in the amount of time and money that they save in overall maintenance. So by actually predicting, by monitoring the performance, you are also in some cases able to predict failure and thus prevent large-scale destruction of equipment. And keep in mind that these equipments are extremely expensive, sometimes costing millions of dollars. So by the usage of AI and ML techniques, we are able to monitor the performance of these equipment. And for this paper, we are focusing on a subset of industrial equipment, which will be industrial rotary equipment. Rotary equipment is essentially any equipment wherein you have things like bearings, any moving, rotating equipment. So basically what we have done is we have used two different data sets. One second. Yeah. So we have used two different data sets. The first is a bearing data set provided by NASA. And this was a bearing experiment conducted wherein they were experiments that were conducted till failure for a bearing this thing with accelerometer sensors constantly measuring the X and Y movement. And so the second data set that we have used is a gear fault data set, which is based on a mathematical model published by MathWorks. And we have actually converted that into a Python script in order to generate our own data set. So the first data set actually has been sampled at a rate of 20 20 kilohertz, that is almost 20,000 data points per second. And for the purpose of this study, we have reduced each of these 20,000 points to a single point. So let's get on with some of the, yeah. So this is the first data set, which is the bearing data set, just an overview of what the data set looks like. So as you can see that over some period of time, the bearing actually degrades, the quality degrades, which results in an increase of vibration. And this is April 18th is when the bearing finally failed, and you will see a sudden spike in the vibration. So what we are essentially trying to do is first, especially with this data set, we did not have any labeled data set. So because it's a supervised machine learning problem, we had to label it by ourselves. So the initial part was considered to be normal, and as and when the degradation started slowly increasing, we changed the classification to moderately and severely degraded. And for the second data set, there are only two classifications, which is that it is either normal or it is not normal. Whenever there are spikes, it is not normal. Yeah, so some of the pre-processing that I already mentioned was that we had to convert those 20,000 points to a single point. For the Gare fault one, which I talked about, there really wasn't much of pre-processing because we actually made the data set by ourselves. So because of which you're able to actually get some clean data. So so what we have done is that yeah, so because with the bearing data set, because it was unlabeled, we actually had to come up with a heuristic algorithm that went through each data point, and as and when it sensed that there was a degradation of data, we actually changed the labeling of the data. Some of the other things that we used was principal component analysis in some cases of this bearing data set when there were multiple features and we had to use only the most important features. So actually the part, as a part of this project, we had also come up with a user interface in order to show the data. And only for that part, we had also used a technique called as LTTB downsampling, which would reduce several thousands of points into just a few hundred points. This was done only in order to be able to display data more effectively. So there were two different models that we had used. This is a mistake, I apologize. So there were two models that we have used here, which is artificial neural network and a recurrent neural network in the form of an LSTM. So the ANN has mainly been used for the bearing data set, whereas the LSTM has been used mainly for the Gare fault data set, though we have also compared the usage crisscrossing of both of these as well. So this is the structure of the ANN model that we had used for the bearing data set. And this was the structure of the LSTM model that was used for the Gare fault data set. We have obviously used multiple dropout layers because there was, in some cases, there were extensive overfitting in the case of the LSTM data set. So the main reason that we actually use an LSTM model for the Gare fault data set is because there's a repeated pattern that keeps coming. So the idea behind this is to actually basically use LSTM to recognize this pattern. And by recognizing this pattern, we are able to predict when the next fault is going to happen. This is in contrast to the ANN model for the bearing data set, wherein there was no repeating fashion. There was just a one-shot degradation of the entire bearing. So yeah, so these were some of the results that we were able to get. There was obviously some sort of overfitting. The model performed very well on just the bearing data set. And however, the main idea behind this model is actually to make sure to see if we could actually train on one type of bearing fault and use the same model to predict failures and monitor performance for a different type of bearing degradation. So this is what we have here. So a little bit about a background about this is that so the NASA data set that I mentioned about basically has three different parts. We are completely ignoring the first part. There were three experiments. We are completely ignoring the first experiment. The second experiment and the third experiments were two separate independent experiments that were conducted by them. And in the second experiment, each of these experiments had four bearings that were there. So in the second experiment, the bearing that degraded was bearing number 1. which is the one to die. Whereas in the third experiment, it was a different bearing that died. So what we wanted to see was if we could create a machine learning model based on the first bearing data set and see its applicability on a case where a different bearing actually died. So in this case, I would say that we were pretty successful. We were able to obtain an accuracy of 98%. And so one of the things that we want to do, if you could see here, is that this correct classification of the normal zone is pretty much irrelevant to us, because what we are interested in is being able to correctly classify degraded and severely degraded zones. And here the model has actually wrongly predicted 20 points that were actually degraded as severely degraded. So in our future work, this is something that we want to look into in order to try to improve the accuracy of the model. So let's move on to, yeah. So the next thing was the Gare fault LSTM. And here we have only two classes, which is normal and broken, because this was a very clean data set, which didn't have a lot of confusion in it. By what I mean by confusion is that it was very straightforward. There were repetitive patterns of spikes. We were able to classify it really well. So basically what I'm trying to say is that both our LSTM and ANN in our case, even though LSTM in many cases is used for predicting using a set of sequences and then predicting the next future sequence, in our case, we have used it in order to classify. So this was the table of results. So apart from these LSTM and ANN techniques, we also used other techniques such as naive-based logistic regression and decision tree. This has not been included in our paper because we wanted to focus more on ANNs and RNNs. Because we believe that ANNs and RNNs are able to perform, have a much better versatility in the sense that they're much more capable of being used in cases which are different from the training set. So this was the model training graph that we had for our bearing experiment. So you can see that basically it's able to get trained within around the first 40 to 60 epochs. And this was the same thing for the LSTM. The LSTM obviously took a little more time than normal. But yeah, so we were able to get pretty good accurate results on both of these. So yeah, so some of the results that can be concluded from this is that through the so the simple multi-layered ANN model that we had worked really well for bearing data over a few. Okay, so and for cross data training testing data sets, the accuracy of prediction was low in some cases. However, previously I showed you that we were able to train on bearing data 2 and able to predict well on bearing data 3. So the reason I bring this point is because when we did try to do the inverse, where we try to train on bearing data 3 and then predict on bearing data 2, we were getting very dismal results of almost only 50%. So this can be probably attributed to the data itself. So that is some research that we will have to do in our future work. And yeah, so in addition, though LSTM network did reasonably for the bearing data set, it was not as good as the single feature based classification technique that we did using an ANN. So in the case of the Gare fault data, the ability of the LSTM model to recognize and classify fault patterns was found to be very high, as the fault signal has a fairly dominant repeating signature. So this repeating signature is basically what you can see here, wherein this is just a section of the data, and this spike that you see is a repeating signature that it's able to, that the LSTM model is able to understand, and hence use that in order to classify the data into whether it's normally working or working in a degraded state. So another important point that I want to bring up is, so some of the comments that we received were that we are trying to monitor and predict manufacturing faults, but the main point of this project was to try to actually monitor and predict failures in cases of operational faults. Operational faults are faults that happen due to continuous use and operation of equipment. So what we intend to do is, the applicability of this is that by using these techniques, you are able to predict the degradation of some equipment before it actually degrades. And this, in fact, helps many of these manufacturing industries and factories a lot, because by being able to tell them when something is going to break down before it actually breaks down, they're able to better optimize when they can shut down the manufacturing plant in order to replace the part or to fix it. Because every day that a manufacturing plant is closed, and if it's a big manufacturing industry, they lose almost millions of dollars. So that is the applicability of this project. Yeah, that's about it. It's a pretty short presentation.
Thanks. Thank you for presentation. Please, questions? Yes, I have one question. Can you show again the presentation that in your confusion matrix?
Yes.
Yes, where is the confusion matrix? You show that on bearing second and third,
yeah.
See, that's not well-balanced classes, so like it's primarily more normal.
Yeah.
And
yeah.
Yes, that's why like why you take an accuracy measure. It's not good for not
yeah
well.
yeah that's something that I've mentioned. Is I've mentioned it actually below the table of results in the paper as well, that when we say 98.2% here, it shouldn't be taken for face value, because obviously, because normal is not the class that we're actually interested in. We're more
Yes.
interested in degraded and severely. If it's able to classify these two, that's what really matters. Normal is irrelevant to us. So this is another reason why like we were not able to basically train the model on one type of bearing defect and then try to use the same model on a different type of bearing defect. So this bearing 2 and 3 basically indicate two different types of defects. So yeah, I agree with you that an accuracy of 98.2 is kind of, it's misrepresentative of what we're trying.
Okay. And have one more question. Is this method is specific to rotary equipment?
So it is not specific to rotary equipment, but we are focusing on rotary equipment because rotary equipment tend to have this, basically the probability of having some vibration-based defect is more in rotary equipment. And where there is vibration involved, vibration is a well-studied subject. So wherever there's a vibration involved, it's more convenient for the usage of machine learning methods. That is the only reason, because what we have found, so basically this project was done as a part of my internship in the company, where the company as a whole, what they do is build machine learning models for the industrial use. So what they have found is that there is no one model fits all. In many cases, there have to be different models that have to be built for that specific equipment. So there is no one size fits all, which is the reason this is only rotary.
Okay, thanks again for answering questions.
Thank you.
And now the next presenter, I would like to present Nikita Koritsky from Russian Quantum Center with a report on learning phase transitions in the ferromagnetic gadolinium ferrum copper alloy. Yeah. Nikita, we do not hear you.
I'm sorry. Now you hear me?
Yes, now I hear.
Okay. So hello, colleagues. Thank you for the opportunity to present my research. on this conference, and I'm going to tell you how we determine phase transition lines in the ferromagnetic alloys. And I start from formulas that you are not supposed to understand fully, but what's important is that we have two sublattices of gadolinium and ferrum cobalt, and we can control the kind of concentration of these sublattices and the magnitude of the external field in which the system situated. And it's known that the system behaves like a ferromagnetic. So it's kind of align anti-parallel to magnetization vectors, align anti-parallel to each other, and moreover, the relative directions are quite complicated. Have a complicated configuration with the change of X and H. And after some assumptions and transformation, we come up with this formula that essentially depends only on concentration, external field, and the angle theta. And it's known that the system stays in this state of minimum energy. So this theta angle provides minimum of this energy, and this angle is just kind of angle between magnetization of these sublattices of ferrum cobalt and the direction of the magnetic field. And if you calculate like this minimum angle in each point, you'll get some kind of phase diagram. This is depicted here. And here we can observe three phases where this magnetization vector and allies are anti-lines and behaves a bit more complicated in higher magnetic fields. And for this case, with assumptions we made, it's rather easier to calculate it numerically. But for more complicated structure with normally distributed anisotropy vectors, for example, it's this approach is inefficient, and we need to provide some better algorithms. And if you look at ML techniques, it's obviously a classification problem where we need to classify like each point to the three types of phase, to one of three types of phase. And there are like lots of proposals. And one of the most promising is so-called learning by confusion. It's combination of supervised and unsupervised learning. And to understand it, we need to recall how like neural network works. We have in supervised manner, we have correct labelings of the data, and we train our classificator. And because we have correct labels, it can learn hidden structure in this data, and this labeling helps it to do it. And so it can give us a high accuracy on train set. But if you put wrong labeling on this data set, this classificator would unable to grasp the hidden structure because you would punish him every time with wrong labeling, and it would be confused. So the accuracy would be much lower. And that's the core idea, because actually in our problem of classification, we don't have any labeling, but we can use this approach because the following way: we have like data of different values, and the task is to find the value of one parameter that is on the phase transition line. So all the data with values of x less than the given goes to phase 1, and that is gray that goes to phase 2. So we can randomly choose some parameter, some value of this parameter, put the labels according to this distinction value, then split on test and train sets, train it, and compute accuracy. And then repeat with another value of parameter and what we're going to observe. So if we have some these parameters and we can observe some phase transition, but of course we are known about this position of the value, but we'd like to learn it. So we can suggest the value x1 to be the minimum and attribute all the data to the phase 2. So put labels phase 2 on all the data. And of course, our classifier would learn it because he would soon understand that he just put labels phase 2 on all the data and the accuracy would be high. But then if we put it like something in the middle of this phase, the classifier would try to learn this structure, but would be confused because our labels put half of them to the phase 1 and half of them to the phase 2. So the accuracy would be much lower. And then eventually when we guess the correct value of the parameter, right where phase transition happens, and the data would be labeled correctly, the accuracy would be high. So by putting enough values of parameter x, we would observe so-called W shape, and the peak of this shape, middle peak, would provide us with the parameter of the value of the phase transition. And we can do it for our problem. Okay, so far so good, but in our problem we have several differences. First of all, we have two variables, x and ash, but in the what I described, it was just one variable. So it's not a problem. We just fix one variable here and run algorithm over all the x's, get W shape, and then switch to another ash. So like a printer, we build a W shape, a kind of generalized one. And also the ridges of the shape would provide us with phase transition lines. Also, we have here, for example, we have multiple phase transitions here and here, and also it's not a problem. We would observe multiple peaks to here. And the most subtle and complicated thing is that we need to generate the input data. If you recall what we had just function and the angle theta that should minimize this function for each x and ash. And to be it more efficient than just general minimization, we use this approach. We throw several thetas, around 20 at each point, and divide the theta that calculates energy in each theta and find the argmin of this value. So we just take minimum of this like 20 thetas, and that's going to be our input data. And so we use XGBoost to as a classifier and obtained this 2D W shape, and you can observe these ridges that resembles as phase transition lines from numerical calculations. And to estimate the precision, we can just take slices. It's like 30 and 250 to observe the general naive W shape. And you can see here that peaks are around accuracy 1 and rather distinguishable from the points around. So we can say that accuracy is rather high of the whole algorithm. And also we plotted as a heat map and put atop lines from the numerical calculation, and you can see that left and right sides that depicts phase transition lies exactly on the ridges of our shape. So we can say that it's the results are coincide. So what we've done, we provided an algorithm for generalized algorithm learning by confusion to the case of ferromagnetic alloy phase transition. Provided rather efficient datasset generation approach, get W shapes and apply and compare it with numerical results. Yet there are some problems. For example, for as I said, it's bottleneck. The generation procedure is bottleneck, and we think we should come up with better ideas about it. And also, of course, it's two example, and field of interest is a more complicated system closer to the reality when we have when the system divided into the cells, and in each cell another TP vector distributed by Gauss, and we need to calculate phase transition in this system. So thank you. I'm glad to answer your questions.
Thank you, Nikita. Yes, please, questions.
So this is Alexander Shapeev. Can you repeat what is your input data?
Yeah, that's a good question. So actually we have like this function, yes, and input data is at each point h and x. Input data is just one single theta from like kind of several thetas that provides the minimal of this function. So we just throw like 20 thetas, calculate 20 energies, and the theta that provides minimum of this function is our input data. And it's really fast, and seems to be enough because we get rather close results with what we expected to get.
Okay, thanks.
And I have a question. You mentioned in the paper that there is a hysteresis phenomena appears in ferromagnetic, but how you handle this?
Yeah. Actually, here I can't answer this question because it was I did this paper with my colleagues, and he's like more into physics, but he's absent right now. So
so the hysteresis effect is like, as I understand, is kind of historical dependence of what we take from the ferromagnetic state. Like it somehow show dependency on the path, how we come from one point to another.
Yeah, but here we just there's no memory of the path on this diagram, on this phase transition lines.
So that possibly, like for future studies,
yes, yes. Thank you.
To see in experimental, that's now it's the model where you data obtained numerically, but if you obtain it from the experiments, like we also in one work in tuning the parameters of how it's accelerator. linear accelerator. We tuned the parameters of magnets to fine-tune the and also hysteresis effect will appear. Okay, thanks for answering. And other questions? Okay, if no questions, thanks, Nikita. Thanks again.
Thank you.
The next presentation, we again came to our schedule, development of water flood model for oil production enhancement. And the speaker is Dmitry Telakov.
Yes, thank you, Evgeny. Good evening, everyone. So I will just share my screen. So can you see my screen, Evgeny? Okay.
Not yet. Yes, now I can. Yeah, please switch to first slide.
Yes, so colleagues, I would like to present you our modeling. This investigation relates to development of water flood model for oil production enhancement. So here the key problem is here this problem relates to production of oil for mature fields. So mature fields has a problem of production that declines with time, and for sure after 5 or 10 years of production, the oil and gas rates declining, and the water production increasing. So here we wanted to see if it's possible to find some connection between wells. I mean, oil production wells and wells that inject water downhole, to see if we can find this connection between wells and to see if it is possible to play with injection rates to increase the production of water and afterwards to decrease the water production, because for sure with the production of oil we also produce water, and for mature fields, as I mentioned, the water production is also a problem, because if you have let's say 90% of water that is going up, you should do something with this technical water, because you cannot just recycle it easily, because normally it comes with some heavy metals, with some even with some acids, with some other things that are really great, that contain some other polluted materials, and it's not really easy to recycle it. That's why the key goal of this study was to see if it's possible with to apply some neural networks to trying to provide some oil and gas companies with some sort of schedule to use to apply on their fields, and to see if they can control the production of oil and reduce the water production. So here the key things that can be gained from this study is, as I mentioned, to reduce the water cycling and to reduce the water that is coming up. Also to improve this water-oil ratio, so to increase the oil production and to decrease the water production. And also it can help to reduce some operational costs, because we can produce more oil, and we know exactly what kind of treatment should be done with oil wells to increase the oil production. Because for sure, it's not only about pumping water downhole, it's also a lot of different operations that are going on. There it's some exit treatments of wells, it's some additional fracture jobs, it's changing of downhole pumps, and also changing of some other things that can help to produce more oil. So that's why our objectives were to provide a model for water flood field using some artificial neural networks. Then we also were trying to provide a model that can explain this water injection and daily production relationship. And also we need to provide some daily water injection rates that can maximize our oil production output. So the methodology that was used is a common one, is a standard process for data mining. So, and we received an access to a big data set of oil production for one mature field that contained around 2,000 wells, and there were around 500 injection wells and 1,500 production wells. So the data was recorded for 10 years, and it was daily injection and production rates. So the data was rearranged using SQL operations and respectively by dates. And then also to make some separation, our daily oil production rates, we assumed that they were affected by 3 days daily water injection, because for sure this is not processes that happen immediately, because if you pump some water downhole, it doesn't mean that you will immediately have some increased oil production. That's why for sure we took some additional lag in this study, I mean for the oil production. Then we also, on this data sheet, we also had some events that took place during the time. And they mentioned it was exit treatment, some perforations done, some reparation of the wells, and they were also included in the model to understand how they can influence the production as well. So the data modeling was done on four different types of neural networks. Approaches. So we used MLP, used CNN, LSTM, and GRU, and to see what will be the best option for this kind of study. So here you can see the model. So here we were trying to understand the relationship between daily water injection and daily oil production. And also it should be mentioned that the data set was increased artificially by 5.6 times, just to have more efficient data set for our models. So on first stage, we developed the function for our model. So the key idea here was to maximize oil production, and then we also had a secondary task to minimize water production. So, but on the first place in our model, we had, so with maximum weight, we had oil production rate. So to maximize the function, we used Nelder-Mead algorithm, and so this was our stage 2. Finally, so here you can see the results, and we've chosen 2 best models. It's LSTM augmented that showed the best mean squared error, and also GRU RNN showed the best accuracy for our modeling. So that's why at our following steps, we will decide which one we will use further for our study. And here we also seen that data augmentation helped to lower the mean squared error and the loss function as well. As for the data, so we can see that the MLP was 63.9% accurate, and the mean absolute error was 13.5. So as I said at the beginning, so the objective was to find daily water injections which will maximize daily oil production rates. And for this one, we've seen that the maximum oil produced per day was around 27,000 barrels more in comparison with estimated in comparison with the previous production. And also it was seen that the daily injection rates should be increased by 90% to increase the oil production as well. But here we can see that the water cut will be lower finally, and the production rate of oil will be much better. So finally, the conclusion can be that combination of different types of neural networks can for sure produce better results. And also, for sure, we cannot right now say what kind of rates and which rates are better for that particular case. But here we also need to understand how the events and how the hydrodynamical model is playing the role here as well. So this is our further studies that we are going to continue. And we would like to understand, we also would like to add some geophysical and geological data here in our model to see the connection. Maybe we can find the real connection between wells, and we can connect it through the hydrodynamical model. And then for sure it will be easier because because right now we have, let's say, 600 injection wells and 1,500 production wells. For sure they all are not connected to each other. We can have, for example, 5 production wells and 3 injection wells that are connected, and all other wells, they are not playing any role here. So that's why for sure it's very valuable for the study to add some geological information, some basic geological information, and then we can play with the data and to see how these particular wells can be connected. So I think that's it. Thank you. And if you have any questions, so please, or comments, you're welcome.
Hi, may I have a question?
Yes, yes.
You studied several architectures for neural networks. And these architectures were designed for different objects. For example, convolutional neural networks are best in images when you have to find correlations between different parts of the image. And long-shot term memory networks are good in analysis of time series. So you found that best networks in your study was LSTM and GRU. So do you have some explanation, some physical reasoning behind this result?
So I think that it can be explained by the data set itself. So I think that maybe the data set is close to the data set itself was more close to this kind of model. I mean the structure of the data set, but really it was some sort of a new study, and that's why we decided to check all possible models to see which one will work better. But yes, Evgeny.
I can also add that really the recurrent neural networks here are working better because the data is represented in time series. So each, like day by day, we have some oil production, water injection. It's given at everyday manner. So that's why, like, it may have some recurrent patterns.
Evgeny, do you think that spatial correlation between different wells is not so important as time correlation for the single well, or not? I mean that it's more important to know how much water you pumped in a specific well than to know how much water you pumped in nearby wells.
As a site study shows that it's also important to have information about neighbor wells, because they may pump water at different levels of like at different
I see.
different structures.
Okay. Thank you.
Okay, thanks for questions. And if no more questions, thank for presenter, Dmitry.
Yes, thank you, colleagues.
And now we will go to the next, and next we have a discussion, and then break, and so now let's conclude. We listened to the four topics, in the very different fields, in linguistics, in equipment supporting, in quantum computing, quantum. Actually, this ferromagnetic was investigated for future usage in quantum computing, and oil and gas also. So, and in all these topics, we see some regression and classification task, and possibly one of the question rises, maybe we can take very new approaches from natural language processing, like when future learning presented in the first presentation. What if we take not only the linguistic data, not only text, human readable text, but if we provide like possibly some instructions of rotary equipment, or we can feed the same networks with equations, with some formula. Possibly we can also extract relations, yeah, or train to extract relations between it. How do you think? I know that one of the investigation was done for computer programs. It's also kind of text which is human readable, but the recurrent neural networks was applied to predict next symbol in a computer program. And I saw also like one of our developer used artificial intelligence tool which completes the Python code. So this actually the linguistic method can also be used in writing new programs. And artificial intelligence can like update itself program by writing some pieces of Python code inside. And actually, so that is the case where self-applicability may rise, may like appear self-awareness of algorithms. Colleagues, what do you think? Okay, so if there is no intent for discussion, we possibly can continue if you feel good, no break need. Then we may continue with presentations. I suggest to listen first the last presentation, remain using computer vision and deep learning for self-recognition. Екатерина Маслова. Are you ready to give the presentation now?
Yes, of course.
Okay.
Good evening, dear colleagues. My name is Ekaterina, and let's start with a small introduction into biological part of our research. Our group study hereditary non-syndromic hearing loss. The main cause for it is connexin 26. 6 molecules of this protein associate to form transmembrane hexameric hemichannels, also called connexons. And typically connexons are located at the cell membrane and dock with a connexon of adjacent cells to form a gap junction channels. that are essential for transport of ions and other low molecular weight between neighboring cells. Connexin 26 plays a critical role in potassium homeostasis in the inner ear, and disruption of these channels may result in irreversible deafness. Different pathogenic mutation in this gene can affect the life cycle of connexin protein in different stages. It can be biosynthesis or oligomerization of molecules, or transport to a plasma membrane, or docking with connexon of adjacent cells. And nowadays, assessment of pathogenicity of a novel variant of genes involved into pathogenesis of monogenic diseases plays a crucial role from medical genetics. And during our previous study, it was a striking finding: a new unique variant is the replacement of guanine with cytosine in 516th position of gene GJB2, and this variant was identified in Tuvinian deaf patients with a high frequency, and this variant meets the main criteria to be classified as pathogenic for autosomal recessive hearing loss. However, the consequences of this variant on structure and functioning of connexin 26 protein remain unknown. Thus, the aim of our study was to clarify the pathogenic effect of a novel unique variant in this gene, identified in indigenous peoples from southern Siberia. Therefore, we established transgenic cell lines with stable expression of mutant variants of this gene and with a wild type of gene as a control. Expression of a green fluorescent protein in these cell lines allows analysis of the presence of target transgene in each cell line, and also allows evaluating of a total number of cells in each line. To assess connexin hemichannels assay, to assess connexin hemichannels permeability, the propidium iodide dye uploading assay was applied. It is known that a high extracellular concentration of calcium ions keeps connexin hemichannels in closed state, whereas a low concentration or absence of these ions stimulate channels to open. Thus, in a medium without calcium ions, cells with functional hemichannels can accumulate the propidium iodide dye and can be detected by microscopy. In turn, cells with impaired hemichannels or in conditions with calcium ions couldn't accumulate propidium iodide and can be detected by microscopy. We obtained a series of images of cells for each of cell line in green and red channels. The red cells correspond to cells accumulated propidium iodide, and the green cells correspond to cells, to transgenic cells. And this channel were used to calculate the total number of cells in each cell line. From 14 to 20 images were analyzed for each of examined cell lines, and in total from 8,500 cells to 15,500 cells for each cell line were analyzed. The permeability of Connexin-26 chemichannels has been estimated as a proportion of propydium iodide positive cells detected on the images. About 74% of cells in transgenic line with wild type of Connexin-26 and about 17% of cells in cell line with analyzed variant accumulated propydium iodide. These results suggest that this analyzed variant significantly reduces hemichannel's permeability. It should be noted that propydium iodide cells on fluorescent images were counted manually. But it is a laborious process since a large number of cells must be counted. Therefore, to calculate the total number of green cells, a neural network software was used. And my colleague Vitaly Kudinov will talk about this. Vitaly, please.
Yep, I'm here. Okay, hello everyone. My name is Vitaly Kudinov. My task is to explain to you some specifications of the neural network, as well as to talk about some of the parameters we chose and why did we choose them, as well as some of the results that we got from the inference of our model. Okay, let me get the slides on here. And let's share the screen. Okay, so first of all, of course, we have to talk about the framework that we used. The idea was to utilize something that is easily installed and set up, which was the MMdetection framework that is made by these guys that are shown on the slides. They made such huge progress in popularizing the ideas of neural networks and how to work with them to basically everybody. And since I'm just a junior researcher, it was very useful for me in order to start working on this project and basically achieve some really valuable results. So not only it is easy to use, but it's also constantly being updated with some of the fresh architectures that are available on the open source repositories, such as GitHub, for example. And since the developers of this framework usually and constantly updated, they have also this fresh and new architectures, which usually show higher accuracies and better results overall. The other point is that they utilize the PyTorch, which is nowadays is basically the rule number one of how to create and train the models of neural networks. So it is faster, more optimized, better working with NVIDIA GPUs. And so that's what they use, and that's what we use as well. Of course, after you train the model, you have to somehow benchmark it and get some metrics. That's why they include some of the tools in order to test the speed of your current model, as well as get some of the accuracy results, which are, of course, for us are very important. So the architecture we used was a cascade mask RCNN model, which was using 101 layers, having a cardinality of 64 and base width 4 of the blocks. What does that exactly mean? So the cardinality is a new type of dimension, basically, that they implemented in their network, which has the idea of splitting the usual convolution path into, well, in this case, 64 different paths, thus trying to increase the variance between each path, and so having some of results being delivered much better than if you just used one convolutional layer and then got the result from it. Base width of 4 meant that they just used 4 convolutional layers in succession in order to deliver the final result and then send it to the next layer. It was also and basically the idea of authors and us in this case was to use a pre-trained ResNext backbone, which is also quite a norm right now to use between everyone. Pre-trained meant that it was already having information about the ImageNet dataset, which is of course better for us since we don't have a lot of data to train our network on, and so we use this pre-trained backbone in our case. The other main thing that this network was using is batch normalization, basically meaning that the idea was to, during training, to calculate the mean and the standard deviation of each input variable. Or, for example, using some mini batches in order to send them to the neural network. Actually, the original authors used group normalization, but the developers of MMdetection, they changed it to batch normalization, apparently thinking that it would deliver some better results, which they probably did already test. And that's what we chose in our case as well. On the bottom of this slide, you can see different implementations of the Cascade RCNN model. On the left is actually the usual one, the mask RCNN from the previous, let's say, version of it. But on the other 3 models, you have 3 different strategies of how you can use the new Cascade architecture. Basically, you just change the position of the segmentation layer after the head outputs its result. So it's either you have to calculate multiple segmentation masks and then normalize them, or you just use one of them in the beginning or at the end. Of course, the other main features are also being used, such as non-maximum suppression, cross-entropy loss, data augmentation, and Adam optimizer. Actually, by default, they were using SGD optimizer, stochastic gradient descent. But in my testing, it seems that Adam actually was delivering better results, since probably our data set was very small and we had a lot of epochs to come through. So just as it seems, it delivers a little bit better. Of course, in data augmentation, there were the usuals, the rotation, flipping, I think color inversion as well. So those are all very useful in our case, since we have such a small data set as well. The other change was the number of bounding boxes for non-maximum suppression, because, well, as you know, the whole idea is to select a lot of high confidence boxes and then calculate the intersection over union between them. But since on one image we had like 1,000 or more than 1,000 cells at the same time, we had to increase the number of accepted bounding boxes for the NMS, which in our case was, I think, 10,000. And only after that, of course, we had a chance of delivering those 1,000 detections on the same picture. So as for the picture, these are just a small crop from the original image of the results that we delivered. But the idea why I wanted it to show to you is that some of the detections, you actually cannot see them, mainly the round cells, the one that which has a shape of a circle. Basically, that is because of the ambiguity of a class definition, mainly this round cell. Because it's very hard to describe why actually this cell is in a state of being just maybe close to splitting or already split it into two parts. And I think Catherine can actually add some more information about this later if she wants to. But that is one of the problems that we actually have in our current implementation. But other than that, the usual cells, they are all being segmented very good. And as well as we added some third class, which is just some of the cells that did not get into the original picture. They only had parts of them cropped by the resolution. So they are just being counted as parts, not as a whole cell. So as for the metrics, the mean average precision with the intersection over union 50 basically delivered around 0.4 on the segmentation, not the bounding boxes, but basically they are the same since the number of detection were the same for both of them, and an average loss of 0.3. So what were the issues? Of course, the lack of experience is the main one for me as well, maybe for other members too. But with the class definitions, of course, as I said, the round cells are very hard to not only computer, but also for people to analyze. Basically, you need a sequence of images in order to get the idea which cell is round and which cell is not round. Of course, the size of the data set, it's very hard to annotate all of those cells, but we did manage to get a couple of images with almost 10,000 of those cells already annotated. But if you improve that number, of course, the accuracy is going to be even higher in this case. And also benchmarking a small number of neural network architectures, because at that time the framework of MMdetection was quite on its early stages, let's say. Nowadays, it's very complex. You have a lot of options. You can try a lot of architectures, even benchmark them at the same time if you have such powerful computer, which we already have. So if we can just benchmark a lot more of those architectures, and especially with the new ones, I think we can, of course, deliver a lot of better results. So that is pretty much it. Maybe Catherine can add a little bit about the cells, the ones that are very active and are ready to be splitted a little bit more. If she wants to. And also we are now accepting some of your questions if you have any.
Yes, Petr, please.
Do you hear me?
Yes, we can hear you.
Okay, two questions. The first question is of metrics that you use to estimate the effectiveness of your classification.
Yes. What about them?
What certain types of metrics have you used?
Well, basically the tool that is included in this basically framework of MMdetection, it allows you to
the
test
type of metrics, the accuracy, the diagnostic odds ratio, or other type of metrics. Please name it.
Oh, okay. Well, I mean, the basic ones are this mean average precision on the bounding boxes and segmentation. That is all. There's nothing else, I think.
Okay. And the second question. you have several channels, so several optical channels
Yes.
that were assessed, the red one and the green one. And you must estimate the intersection of these channels for some types of the cells that are not leaf, in the case of the propidium iodide positive cells, but have the signal. And these cells must be accounted as another class of objects, in contrast to the cells that have only propidium iodide positive color or green color, as I understand. Did you use some procedures that merge channels or modify channels by brightness contrast curves or not?
Unfortunately, I did not yet tested completely the red channel, so it's now only working great with the green channel, the cells were still alive and running. But I mean, I annotated some of the red channels as well, and I think it will not be a problem to add them as an additional class of, like, you know, dead cells, the one that are not moving anymore.
This is a very important problem, because you must use some type of merging procedure, and you must think about it, how to do it effectively, as you have another type which has another merge of colors, but neural networks do not work well with the color information, as you remember. And another small question on the form identification, which was mentioned by you. Do you plan to use some image modification procedures that rise contrast brightness curve, or some manipulations on the image that use the first производная, не знаю как.
Derivative.
Yeah. The first derivative from your image information. This will provide you a more specific information on the borders of your objects.
Okay. As far as I know, there are some normalized techniques already being used in order to augment the pictures, but it's not a problem to add some additional ones, because they're just using, you know, the standard OpenCV library. So whatever is available there, you can use in this framework.
That's a very important problem, that sometimes it is useful to modify an original OpenCV project, but there are no possibilities to do it, and it must be done somehow. I don't know how we.
Okay, got it.
Thank you.
Thank you.
Okay, thanks for your presentation. And we now change the moderator. Now the session will be moderated by Akhilesh Srivastava. Akhilesh, are you here? We do not hear you. Akhilesh?
Hello, can you hear me?
Yes, now we can hear you.
Okay, thank you for the introduction. So our next paper will be about pattern recognition for bubbly flows with vapor or gas liquid interfaces using UNet architecture, which will be presented by Rusmat Mulyanov, if I got the pronunciation right.
Yes, it's another teammate of Rustam Mulajanov, Seryotkин.
So we have pattern recognition for bubbly flows with vapor or gas liquid interfaces using UNet architecture, which will be provided by Rustam Mulajanov, given as a speaker. He presented under the topic of multi-phase flow.
It will start 20 minutes later. Perhaps he will be at 19:20.
Ah, okay. So probably by schedule. Guess it's not joining yet. Okay. So in that case, shall we proceed to the next person who is available in the meantime? Using computer vision and deep learning for cells recognition by Andrei Matviev.
No. Cells recognition already given. Yeah. It's for nanoparticles recognition.
Then we have Facemask detection using MMdetection.
It's already given. Actually,
already given. Okay.
Yes. So the presentation on nanoparticles recognition.
Yes. Okay. I'm ready. Yes.
Okay, please.
Hello, everyone. Today I'm going to tell you the topic using computer vision and deep learning for nanoparticle recognition on scanning probe microscopy images and our modified UNet approach. My name is Mikhail Lis. I have worked with Aleksei, Okunev, Anna Nartova and Andrew Matveev. This work was done in a collaboration with Boryskov Institute of Catalysis. In this slide, you can see my plan for today. I will start with the introduction. After I will talk about problem statements. After that, I will discuss our approach of UNet network, and I will finish with the results we obtained so far. To evaluate the effect of the catalyst on particles, nanoparticles, several parameters must be calculated. One of the main characteristics of the activity of the catalyst is the turnover frequency of the reaction, which is calculated by the formula that you can see on this slide. In simple words, we need to calculate the number of particles in the image and the distribution of particle sizes. Our goals you can see on the slide. We want to develop a custom method for our dataset and analysis of results. And what we have 10 images for training, 3 images for test, and we use the mean average precision as a metric for instance segmentation. Here on this slide, you can see data examples. As you can see, these images create several problems. The first one is that images are blurred and particles overlap each other. And the second one, images contain artifacts due to the microscope work. On this slide, you can see the screenshot of the program that are used for data labeling. In order to define the margin of the particles on such a blurred image, we need to define the borders by using the intensity distribution, and now it's manual work, which takes a scanner operator up to several days. And what about UNet? We trained the UNet network to segment nanoparticles, nanoparticles boundaries, and anything that is not nanoparticles. That means their background. In this and in the next slide, you can see masks, which we used for training. In this slide, you can see the main mask and border mask and background mask. We used efficient net B3 that was pre-trained on ImageNet with noisy student as an encoder, and the neural network was trained in 2 stages, the main stage and the boundary stage, and the boundary search stage. And the trained network was used to obtain 3 masks mentioned earlier. And at the first stage or main stage, the network was trained 100 epochs with the initial learning rate 0.1000, and the learning rate was lowered twice if the total intersection over union metric for 3 channel on validation did not improve for 5 epochs. And as a loss function, we use a combined loss consisting of the sum of dice loss and focal loss. At the second stage, we used the same training method as in the first stage. The only change in this stage is the loss function. We noticed that during training in the main stage, the intersection over union metric on the channel with borders reached a plateau on the 10th epoch, while on the remaining channels, the plateau was observed only from 50 epochs. And we decided to train the network by making a weighted combined loss. We counted the loss separately for the channel with borders and for the other channels, and added them up with weights of 0.8 and 0.2 respectively. And this gave us an increase in the intersection over union metric on the channel with borders, as well as an increase in the total intersection of a union metric across all channels. And the network encoder was pre-trained. However, the decoder weights were installed randomly, and we also conducted an additional experiment. We used an open dataset with labeled cells in order to pre-train the UNet network on this data. And the network output is a 3-channel mask, from which we needed to get a single-channel mask. First, we used the softmax function on channels, and we go to the probability space, and then we multiplied the channel with a mask and the channel with the borders, and after inverted with respect to 0.5 and threshold the results of the product to get seeds. and threshold for seeds in our method was 0.7, and we also had a threshold channel with a mask. This threshold in our method is 0.4, and we used this newly masked and generated seeds as an input to the watershed transform. So in this slide, you can see example of the final results for one image. The mask looks good at first glance, but there are some inaccuracies. You can see, for example, for this example, there are particles that are stuck together. For example, in this shape shows that there shouldn't be several particles and not one. And this table shows the results of particle recognition in ordinary UNet network and by modified UNet with the method we proposed. The table shows that our method significantly improves the usual UNet, and the results of the proposed method with pre-train and open dataset can be also seen in this table, and mean average precision became higher, but still is not enough as compared with state-of-the-art map of about 40%. We attribute it to the small size of the training data set, and one more reason is that masks were not resolved as individual particles by UNet network. That's all. Thank you for your attention. Maybe someone have questions.
Thank you for your presentation, Liz. I have a question myself, if you don't mind.
Yes, of course.
Okay, so I get that your work is on pattern recognition. It's on a particle recognition, rather. So you actually recognize the boundaries of the particle and you try to improve the precision, if I'm not wrong. That's what your work was about, right?
Yes, yes.
Okay, so could you tell me where this could be applied in future, like a real life example?
Yes. How I said, this project was with collaboration with the Institute of Catalyst, and this work have some service, and we have a site where the researchers can go and load his images and download the results of the segmentation. This service we have already done.
Okay, thank you. Any other questions?
So, colleague, I would add about this site. So, but I may show this in action maybe now or maybe a bit later in discussions.
If it doesn't take too much time, you can show us all. Thank you.
Okay, so how can I do this? Mikhail, can you close your presentation, please? Thank you. So can you hear my screen? Can you see?
Yes, we can see.
Yeah. So this is our first page. So here it is. It's online series, and it was made for microscopists who needs to calculate the particles, their size, and so on. So there is a video tutorial. The user can see this. User can read the instruction. So how to use it? You have to go to the first page. You may register, but now I'm already registered, so I can show you the files. So there is a list of the files which already be used. So, and if you want to calculate, to process your own picture, you have to open it in BMP format or JPEG and so on. And you can load your picture, upload it to the system. So it's the original picture. So here you can choose the model. So this one is the last, is the more or less best. We are working to improve. And for example, Mikhail Liz showed one of our attempts, which is used UNET, because all these models use masker CNN method. So, but let's go further. You have to push the process button. So there is a processing of this picture. You have to, after refresh the page, you can see the results. Here is the recognized particles. You can see here the files which is formed after this. So this is the distribution of the particles by the sizes. Here is written some statistical results, the average size, and so on. So I wouldn't say I would talk much about our results. So if somebody interested, I can explain in details. But so in general, we have some peculiarities of our online service. For example, so you can see here the JSON file. It's a special file which you can open in Label.me program. And if you don't like some contours which was recognized by a network, you can delete it or just to make it better, for example. And again you can put this already corrected file in our system and to get the corrected statistical results. So in short, this is how our online service is working. So.
Okay, thank you for your presentation. Any other questions?
And I will also add that if you are interested in network that Ekaterina and Vitaly told and Mikhail Liz, they are present at the site. The first is already present, and I believe Mikhail's new version will be a bit later.
Any comments from anybody?
Yeah, if I could. Is that okay?
Sure, please.
Thank you. So I have a question to Michael, a little bit about the architecture and especially the pre-training process. Basically, I'm interested in if you only have changed the last convolution layers, or did you basically just use the classification layer in order to fine-tune it to your data set? So like which exact part did you fine-tune to your own data set? That is my question.
No, I have the several output from the model in open source dataset and my dataset. I have 3 masks in the output, and when I pre-train and after that I not change the network. If I understand your question, yes. No?
So you mean that you do not touch the UNet convolutional layers anymore? You only change the classification layer, and that's what you train after, you know, presenting the input data of open image dataset and everything else as well.
Sorry, you mean that what I change in the neural network, or what I changed when I train in the open source data set, and when I go to the my data set?
Well, okay, let me rephrase it a little bit. Basically, at first you have your, you know, initial architecture. You don't have any weights trained on any kind of data.
I have pre-trained encoder. I have pre-trained EfficientNet B3 with from ImageNet with the noisy student technique. I have pre-trained encoder, but I have random initialized the decoder weights.
Okay. So basically, after that, you only train the decoder, and encoder you do not touch anymore.
No, I train I train all network, but I train with some, for example, 20 POH with freeze encoder, and after that I train with unfreeze the encoder and train all network, and after I train network on my dataset.
Yeah, okay, that is exactly what I want to know. Thank you.
Okay, thank you for your question.
Mikhail, and in simple words, what is the main idea of two-stage studying?
Yes, in simple in a simple words, we when we train the only one stage, we have bad accuracy on border channels, and the first stage needed to train the main mask channel and the background channels, and first stage needed to train the border channel.
So if we use one stage, the network learns how to predict the particles roughly, and you first teach it.
Yes, we we see the metrics for each channel and metric for all channels, and if I see metric of all channels, I didn't see some changes, but because the positive classes in the channel with borders are on average 3 orders of magnitude less than in the other channels, and so on. In this channel, the loss was obtained less and made a smaller contribution to training, and because we have a second stage.
So this is because borders have less pixels.
Yes.
Okay. And whether this is usual approach or this is your invention? I didn't notice it.
Usual approach for what?
For such tasks, segmentations. Because I didn't see it in papers.
Approach, you mean that a network for instance segmentation or for UNet in instance segmentation?
This approach of dividing masks by border, not border, and pages.
Yes. The instance segmentation have some approaches. The first is use the network semantic segmentation network, and after we can try some post processing, or we can in the paper, for example, segmentation is all you need. This approach used for search bounding boxes. The same approach, not exactly this, but the same. And the second approach is anchor-based network for instance segmentation, and the third approach is anchor-free networks for instance segmentation, like center mask. That's all.
Okay, thank you.
Thank you for your question.
Okay, thank you, Liz. The next presenter will be Rusmat Mukul for pattern recognition with vapor or gas liquid interfaces using UNet architecture. Do we have Rusmat Mukul?
It's probably me instead of Rustam.
Okay. Please go ahead with your presentation. It's pattern recognition for bubbly flows, right? With vapor.
Yeah.
Okay, please go ahead.
1 second. Okay, could you see it?
Not yet. Now, yes.
Okay. So, hello everyone. My name is Alexander. I will present our research group from Novosibirsk University and Institute of Thermophysics. And today's topic already was mentioned: pattern recognition for bubble flow with vapor or gas liquid interference using UNet architecture. So first of all, in last year, it was a couple of works based on recognition bubbles using machine learning techniques. First of all, in the first work on the left, it was shown that it was compare correlation method of fine circle bubbles with neural network methods, also that find only circle bubbles. And you could see even on pretty difficult images, like both methods far away from perfect, but the neural methods could find more bubbles. Other work showed the problem of overlapping bubbles. The situation where one bubble overshadowed another, so it's difficult to estimate the size of the background bubble. So they research this problem. And the third work that this was published in this year was basically the really like not simple, but two steps architecture of neural network created especially to recognize bubbles from image. So the first step was to basic regional convolution network to recognize a single pattern, single bubbles with a rectangle, and then each rectangle was like increased precision of what's happening here with elliptic shape bubble. So they found the central position and main axis of this ellipse. But we don't like this. All these methods that all this works that I talk about, they limited by the shape of the bubble, either circuit or ellipse. So we want remove this limitation, but not increase the complexity of the network. So we decide to use the default segmentation task. So it's basically a segmentation task for image, and we use UNet architecture for that. So input was image, colored image. We use a backbone or encoder, pre-trained ResNet network. After that, as UNet goes, it goes like we remove the last flattened layer from this ResNet. So we get bottleneck, like this is where all information should go, and then decoder expands this little information back to output into 3 channels because we have 3 different classes. I will speak about it later. So it's basically the classification task for every single pixel. We use the according matrix, which is error for every pixel. And as UNet goes, we also add steep connections. Sorry. Yeah, we train it. We took, as I told, pre-trained network and train it on 20 epochs. It was enough to reach like 99% accuracy on validation data. And what images we use? Our colleagues from physicists research bubbles, and they have 2 setups which they generate images from. So on the left, they have part with water and a heater at the bottom of it. And the feature of this setup is that the heater is transparent. So the camera actually goes from the bottom, so we could see the surface where bubbles generating. Light source comes from the top, so we could see like the shadow of the bubble while he sits on the surface. And those physicists research the heat transfer from bottom to the top, and the vapor bubbles parameters of these bubbles generate the heat flow. So it's important for that reason. And the second experiment set up on the right, so the flow of bubbles going in the flow from left to right, and initially all the bubbles generated about the same size, but during the flow they collide, so they could merge or they could split. So it was interesting how the size of the bubble evolved during this transfer. And the camera look at this area, which red area, and it was also the step here, adjusted technical features of this setup, so we could see it's like the camera could see the actual bubbles. So the sample of images from both experiments shown on the slide. So on the left, you could see the bubbles sitting on the surface, also the bubbles already out of the surface. And I must say the focus here is on the surface itself, so the bubbles already moving up is out of focus. And on the right, those bubbles just moving right, they're all in focus. Of course, we cannot see movement on a single picture. And to recognize these bubbles, some mask was created manually To be precise, those masks was generated with gradient algorithms first, then manually, so human improves this mask, corrects some mistakes that the gradient algorithm does, and we could see the difficulty here on the left side because we have bubbles that's overshadowed by another bubbles going up, but they're not on the surface, and the mask supposed to go to the masks supposed to go bubbles only that's sitting on the surface currently, and we decide to go with three classes: background, border, and bubble itself. It's supposed to help recognize the bubbles in case they overlap, particularly over each other. So the border is supposed to help them. So the images didn't match the UNet input as it is. So we split them. So we split the original image into squares, 256 pixels each. But it could be a problem on the borders because the bubbles like cut. It could be a problem because neural network could, it high chance to mistake in this case. So we decided to use only core of each regional and overlap those samples on each other. So we actually split image into sizes of 192 pixels. We use the only middle part of this pixel, but crop a bit bigger part of the pixel. After that, we independently each part was going through network, creating the mask, and the results was conjunction together to create the mask for original image. In this picture, I overlap the mask and the image, so it would be more easy to realize what's going on. And this is the full image, the results. Green lines is the cut lines, as I told before, for both experimentals. And we could see that background bubbles didn't get the mask because they're not what we're looking for, which is correct. And if you look closer to evolution of the bubble, because if we process the video, several images in a row, so bubbles start small and the phase of rapidly growing. At some point, the size start to decrease, and when we don't see, I don't know how to say, I show in the middle, the first frame when the bubble detached, we could see the small eye in the middle. And it's really tough to recognize with like normal methods, with gradients. I show the history, the gray area, which was done by gradient methods or such. And we could see that actually bubble detach happening like here. And it's tough to say on the curve itself when it's happened. So that's basically why that's why we expect network helping here. And what else? So we process about 100 of images with that network to study how the bubble grow, so the growing process and the detach process. And we could see on the left side the depends of how the diameter grow, and we actually could see the network results, the manual measurement where just human sees the diameter of the bubble like by hand, and the theory. And from the second experiment, there was so the initial bubbles was about the same size, and this is the biggest bin on this graph. And after that, we could see the sizes which twice as bigger. That means of the merging of two bubbles. That's not twice because it's diameters, but we actually double the volume of the bubble, but we could see the diameter here. And then we have the other harmonics of the sizes, which like 2 bubbles, 3 bubbles, 4 bubbles, etc. So going to conclusion, we show how we could use segmentational network to recognize bubbles from images. It used ResNet. It used UNet with ResNet pre-trained networks as a backbone, and pixel by pixel segmentation. It didn't use any like, circle or ellipse or other pre-trained shape of the bubble. We trained it with 3 classes to recognize overlapping bubbles, to give the network possibility to recognize bubbles. And we demonstrate how we could track bubbles between several images, how we could track the growing process of each bubble, and studying the flow of the bubbles on the second experiment, how the size of the bubble increase, and the situations where there's some bubbles merge to each other. That's it for me. Thank you for your attention. I would answer a question.
Thank you so much. I have a question myself. So in your experiments, you used water as a liquid medium.
Yes.
What if I want to use a different liquid medium like glycerine, which has a different viscosity? And of course, like the process of bubble formation would be pretty much the same. But if I were to use a different liquid medium, let's say like glycerine, would you like start experiments from the beginning, from scratch? Or would you use your trained neural network model to predict the bubble formation for glycerine? So how would it be?
Unfortunately, I cannot tell you how different the images would be. What I would do if I would look like with my eyes on the image of water medium and glycerine to see how they distinguish like from human perspective. And if they're going to be pretty similar, I would say it could be used without any changes. If they different because of light reflections, it must be retrained, of course.
I get it. So you must start your experiments from beginning if you're going to use a different liquid medium.
If it looks different, yes, because it's image. That's what matter.
Okay. Any other questions?
May I ask?
Yes.
So again, thank you. Can you tell me what kind of signal did you process? Video signal or pictures?
Pictures. Each picture was processed independently.
And how did you make tracking of the bubble?
That's a good question. So we have a pretty good time resolution. So we could, so every time we find the bubble, we could find the connected area to this bubble, find the center of mass of this bubble, and the effective, so the size, and we could, effective radius. So if the shape would be a circle, we could extrapolate the size to find the radius. So after that, we could track the center of mass from frame to frame. Because we have a good time resolution, we could go to the some threshold. We guaranteed that bubbles don't go farther than, let's say, 10 pixels, because it's unreal from the setup. After that, we just tracked each bubble frame to frame and collect data, collect history to finally create this statistic.
Did the bubbles move on the surface?
You mean from image perspective, not only to depth, like to left to right, for example?
Yes. Yes.
They could move, but this movement is really slow. So have several pixels threshold, would guarantee it. So for example, bubble cannot move like further than his radius. And I'm talking about the left, the first experimental. On the right experimental, they of course they move to the right, but once again, the time resolution is pretty good. So we could just find the closest bubble and be pretty much sure it is the same bubble.
Okay. And how long did you analyze your video for your result? Because you told that you have very high resolution, and so I can imagine that you had to recognize very many pictures.
We have high resolution, but not really long videos. So the number of frames was, so for train we use around 500 images, but of course each image was split into sub images, as I told. And the statistic for results, we used about 100 images. So it's like several hundred bubbles. So it's the training takes like half an hour, maybe something like that. So not really long. Any other question?
Okay, so in that case, I guess it's the time for discussion.
I have one more question.
Okay.
So by counting and tracking the bubbles, what the actual task you are solving, and how estimate the quality of this task?
So unfortunately, I'm not the physicist who told how the bubble growing process could change the heat transfer, but it's
yeah. So the question is the particular your contribution to according science. Like previously, bubbles were calculated and counted like either by simpler methods, not accurate. And now, what is like possible contribution to the corresponding science will be usage of your algorithm?
Okay, so as I told, it's really important to recognize only bubbles that sit on the surface. And it's tough to distinguish with, let's say, correlation methods. The bubble that's exactly on the surface, that's already detached from it, as you could see in this video once again. So this moment right here, it's impossible through correlation methods to find. And other thing is the bubbles, like the other models use spherical, like the circle or the elliptic size of the bubble, but we use the area without assuming that it's a circle. So it could be like any area. It's really important on the second experiment with the bubbles flow. The shape sometimes could not be described by ellipse. It would be too inaccurate. So that's to like distinguish from previous works.
So as I understand, please correct me if I'm wrong, that with this method, you first ever made possible to solve like the vapor bubbles like detecting on the surface, which was not possible previously.
No, of course it was possible. We use a technique from, so this technique doesn't apply to these bubbles before us. And we show how effective it could be to use pixel by pixel segmentation to recognize bubble shape. So it was done before with other technique, and we show that this technique has some advantage over previous one. but we use previously known methods. These methods also like wisely used in biology to separate cells in the blood, or like to distinguish different cells from each other, so to count them basically. So it's not a new method, but it was firstly implemented to bubbles.
Okay.
Okay, so I guess if you're not going to have any more questions, I guess we'll go for discussion. And like Professor Evgeny Pavlovsky earlier stated about a possibility where we could have an artificial intelligence technique to complete Python codes, which was very interesting. So from the previous three papers, from my perspective, if I may, with your permission, we saw about pattern recognition, about finding the boundaries of a microscopic cell, or finding the boundaries of bubbles that we saw earlier. Since I was a mechanical engineer earlier, a couple of years ago, maybe I feel there is a certain application where we could try to create a warning system using this artificial intelligence techniques. For example, like when we need to keep a chemical below a certain temperature, if it starts boiling, then we could create an artificial intelligence technique that could give us the warning before anything happens. So the thought just struck me. That's one of the applications that I can think about. But otherwise, can we have a brainstorming topic of other potential applications of how these projects could be used in further science, how they could be developed? If anyone is welcome.
Yeah, actually, there's almost everywhere UNet approach was used for segmentation. And initially UNet was like invented by processing medical images. And especially, as I remember, it was used for MRI images to detect cancer. And that was UNet approach appeared, and then applied successfully for different other, even micro and nanoscopic scales, as we see now.
Guess in that case we could apply it for COVID as well.
Yes, sure. So that's a very powerful technique, and maybe we need to go from microscopic to megascopic scale, like to investigate big things in astronomy scales.
Probably the bubbles look like stars on the sky, so astronomic could be like.
If I could add a little bit, yeah, to this.
Please, you're welcome. Please.
Yeah, thank you. Well, of course, I mean, the main application for all of this is to accelerate the results, because the time we spend ourselves to do all these things, if we could, transfer all these tasks to the computer, of course, it's going to be a lot faster usually, and maybe even more accurately if we are talking about medicine, because sometimes, there's such a thing as a human error, so it could happen. But I mean, other than this whole medical idea, and we are talking about just the pictures, the one that we get, we can also analyze three-dimensional data, because that is actually very important, not only in medicine, but also in other, basically, what's the word? I forgot. Other directions, other applications for it. So I think other than changing the architecture of the neural network itself, maybe there is an idea of optimizing the speed of execution of this algorithm, and maybe even something like quantum computers, if it could happen in the near future. So if you could, rewrite the architecture to the idea on being executed on a quantum computer, it could potentially have an even bigger increase in performance rather than just using our usual computers and graphics cards and everything like this.
Anyone else with their interesting thoughts and directions of how these works could be applied?
I suggest one more idea. Like in medicine, there is a notion of biomarkers. So that is somehow like some computed feature which say a lot about some issue. And for example, if we see a bubble, then we describe bubble by two parameters. Shape it's usually circle. Sometimes if it's different pressure from different sides, then it may be ellipsoid, or in fast flow it can even be not elliptic. So anyway, we know that we involve our human knowledge that bubbles are usually elliptic. So we can describe bubble by two characteristics: center of mass and second, the radius, or three parameters, two radius if it's elliptic. So it's kind of a priori or some knowledge about the structure of the bubble. But this knowledge is not given to the UNet architecture. It's not given to the neural network. Neural network tries to discover its features, by a lot of computations, a lot of small experiments, and we use pre-trained network to do this job. So possibly in future we'll get into how the UNets or how the deep networks discover these initial features and can bring us to new knowledge how new objects can be described by the minimum of characteristics, for example.
That was a very interesting suggestion that you made.
So basically, instead of having convolutional layers, you want to have something like bubble layers, whatever. Rewrite basically the activation functions in order for them to describe not just regular shapes, but complex shapes, if I got it correctly. So yeah, I think it is, well, quite possible, if not already. So all you have to do is just to rewrite the idea of creating this solution to the mathematical problem, which is very hard for me to understand because I'm not really a mathematician, but for those who are, I think it is very easy. So if you could assemble a team where you have your data scientists and mathematicians, I think it would be a really good task to do.
Anyone else with their suggestions?
Oh, may I add a bit?
Please, you're welcome.
So I would show the results. So yes, let me switch on the screen. So After we trained our network on nanoparticles, which you can see here, we just for fun tried to put any other pictures which look more or less the same. So, and in principle, our trained network can process these pictures. So, for example, here you can see the quantum dots. It's physical objects, which more or less the same as the nanoparticles, but in principle, it's not it's not the objects on which our network was trained. So also we used other pictures. It's particles, and also our network can recognize in general more or less the pictures. So you can see that the boundaries is not the same, not all of them can be recognized. So this is erythrocyte. I'm sorry, I'm not a biologist. I don't know how it's to say exactly. Erythrocytes. This glycocytes. So these are the viruses. So, and this you know already, it's cells. And we also give to our neural network. So this is a picture of the ships from the quadrocopters. And also our network can recognize some of them. So, and the main conclusion is that in general, neural network can see something, can recognize something, but the accuracy is not very good. And as just for the case of bubbles, this presentation which we saw from the Institute of Thermophysics. So you can see that in every specific task, anyway, you have to take the neural network and train for the special objects which you study. So this is what I would like to say. Thank you.
Yeah, I think that's great. Yeah, see if it's like transfer learning. Yeah, we not learning, just transfer. You just apply for different never seen objects. Easily increase the general set of possible applications.
Okay, thank you for your contributions. It was a very worthwhile discussion today.
Could I add something?
Please.
I think it is the same as using pre-trained like backbone for UNet. It's not like nothing special that's used. It could recognize different shapes as long as it's like the quality. It's still acceptable, but it's a bit worse. And we use train to increase the quality as high as we can. So it's pretty reasonable what you just said.
By the way, isn't it possible that some features which were taken from ImageNet, some tricky arcs or something, can be activated by different objects? In our particles, they are 0, and the output is 0, but maybe some combination of not used features appear. And
when you show small logo of Google, then it activates special neuron here.
Yes, I think that is.
And deactivates all the network. Or special call to national security system. So I want to show that tomorrow's schedule. We starting at 1 p.m. at Novosibirsk time. And there will be two sessions. First with natural language, bioinformatics and inverse problem applications. And second, in applications to graph analysis and community detection, and in geophysics, also with the help of convolutional neural networks. And also we'll finish tomorrow by the report on reproduced works. Some works were applied to reproducibility, by which we check availability to reproduce paper results. Almost like that was interesting, not 100% reproducible.
With bugs and typos.
Yes. And also all today's session was recorded, and it will be processed by artificial intelligence, and we'll see tomorrow the result.
Okay, thank you.
Thank you.
Thank you. See you tomorrow.
Say goodbye for collective photo.
Thank you, colleagues. Bye.
Bye.
Goodbye.
Goodbye. Bye.